I forgot to register apparently. So. Are you seeing it on the Google Meet?
Oh, yeah. Try to join that.
We got one more minute on the clock here. Give everybody a chance to filter in. Sorry,
Looks good.
Cool. Right, we can go ahead and get started. Thanks all for coming this afternoon's session where the theme is land-atmospheric interactions. We'll go ahead and get started with Meg Fowler, who's going to talk about land-surface heterogeneity, subgrid cell, and how it affects updrafts.
Awesome. Thanks, Sam. I love everyone trying to say heterogeneity. It's like my favorite part of my topic. So I want to take a moment just to acknowledge all the co-authors who have contributed to this work in previous versions as well. But it's a growing list, but hopefully everyone's contributions is recognized and valued. What I want to talk about, as Sam mentioned, is how we can look at the sensitivity of atmospheric convective updrafts to subgrid scale land surface heterogeneity in CESM2. So if you've been in my talks, you've seen this slide a million times, but I'm a big fan of repetition. So when we think about land-atmosphere interactions, what I want us to keep in mind is the picture on the right-hand side, where we have a heterogeneous surface that has different land surface types. Each of those has an atmosphere above it, and there's a ton of mixing and interactions that's happening. So you can picture this as the real world, where surface heterogeneity helps us set up boundary layer cumulus clouds, depending on kind of where you have wetter or warmer patches at the surface. It can set up mesoscales, secondary circulations in the atmosphere. So when you have these gradients at the surface in moisture and temperature, what ends up happening is the atmosphere wants to equilibrate those gradients, and so it sets up this overturning circulation. And a recent study from Jason Simon in 2021 showed that can even impact things like liquid water path and turbulent kinetic energy on scales of about 100 kilometers or so. Now the model world is a little bit different. So the model world is more like the picture on the right, where we have interesting heterogeneity at the surface, but when we're thinking about the ways in which the land and the atmosphere interact with one another, we're really only passing grid mean values. So we're averaging all the fluxes together, all the states. The atmosphere essentially sees a homogeneous surface. So moving beyond this is the goal of a climate process team called CLASP, which stands for the Coupling of Land and Atmospheric Subgrid Parameterizations. It's been going on for a few years, and so I want to share some of the results we found. And one of the goals of CLASP is kind of designing a new strategy, where we're linking existing representations of subgrid heterogeneity across land and atmospheric model components. But I do want to put a little asterisk here on new, because I've been talking about this for 2 or 3 years. It's not exactly the newest thing anymore, and so I want to kind of give you a bit of background. We tried a first attempt with this a few years ago. The paper in CESM was actually just published today on James, which is really exciting. Thank you. It's 2 years of hard work. But it's also out from Meng Wang in 2022 looking at E3SM, so you can get 2 flavors of what's happening with this. I won't go through the results on like the methodology and how we did this, but I do want to highlight something important. So when we try and implement a parameterization, our goal is to match something like LES or observations to ensure that we're capturing a process that we were missing before. So here I'm showing you an average of 60 high-resolution LES simulations, so large eddy simulations, looking at the difference on the right-hand side between a heterogeneous surface and a homogeneous surface. We're looking at temperature variance throughout the vertical profile of the atmosphere on the top, moisture variance in the middle, and then turbulent kinetic energy on the bottom. So you don't need to know what any of those things are. What I do want you to know is that when you add in heterogeneity, all of those things increase. So we have reds everywhere, there's these stippling, which indicates significance. So in large eddy simulations, the atmosphere is sensitive to whether or not you have a homogeneous or heterogeneous surface. This is what happens in CESM. These are not the same, right? So in a series of single column CESM simulations where we're prescribing a heterogeneous or homogeneous surface, what we found with our first attempt was that any response in the atmosphere is really limited to the lowest model levels. We don't really see this huge atmospheric response. So we went back to the drawing board because ideally we want to see something more vertically cohesive like we see in LES than we saw with our first attempt. So the good news from the land modeling side is that I haven't changed anything in terms of how I'm treating heterogeneity from the land. So you can imagine we have this grid cell, and this is actually the grid cell I'm going to show you later, so good news. The grid cell is evenly split between lake area, urban area, grass, and irrigated cropland. Within CLN, those are kind of represented statistically, and so we don't know that they're all connected, but we do know that each of these individual surfaces has unique fluxes and states that arise from them. Now again, because of the way that we're passing information between the land and the atmospheric model components, the atmosphere has no idea of this, right? The atmosphere is taking all of that interesting heterogeneity, averaging it together to one value and saying, here's your surface. With that, the atmosphere is doing other fun stuff with heterogeneity. So within CAM, the Community Atmospheric Model, there's a parameterization called CLUB, which stands for the, no, we're not gonna do what it stands for. Got myself there. But it's basically the boundary layer turbulence shallow convection parameterization that's in CAM 6. And that was our attempt one, was let's just use CLUB and see what happens. Nothing great. So there's a new development, CLUB MF. MF stands for mass flux plumes. And it was developed in 2022 by Michael White and others who are here at NCAR as well. The idea being that CLUB, being a shallow convection turbulence parameterization, kind of handles small-scale overturning eddies. So it's just kind of that more random motion you see in the boundary layer. The mass flux part actually captures organized updraft plumes, so it's capturing what's stronger happening in the boundary layer in a more organized way. So CLUB MF captures heterogeneity by initializing a number of these updraft plumes. They're initialized from the surface, which in this case is homogeneous, based on whenever the grid mean buoyancy flux becomes positive. So if you can imagine in the morning, the surface is heating up, say maybe around like 7 a.m., the surface in a grid cell mean sense gains a positive buoyancy. That means however many plumes you can initialize, say 10, are going to be initialized all at the same time, and they'll shut off all at the same time at night. The plumes undergo stochastic entrainment, so there is some heterogeneity within the plumes. Some can grow higher, some can grow smaller. And eventually the buoyancy flux hits zero, the plumes stop growing. So what I'm proposing with kind of attempt number 2 of CLASP is what if we just remove that intermediate step? So rather than averaging everything up from the patch level, passing a grid mean value, what if we initialize those updraft plumes over individual surface tiles with their unique fluxes and states? So you can imagine maybe the lake patch has higher latent heat flux, it should initialize moisture plumes. Urban patch would be drier, initialize drier and warmer plumes. So how do we test this? We have a series of single column SCAM experiments. They're focused at the arms within Great Plains site, and we're looking at the warm season, 2015, 2016, June, July, and August. So that's when land atmosphere coupling tends to be stronger in that region. What I will note is that the Southern Great Plains site by itself is actually fairly homogeneous. It's mostly grasses and crops, not the most interesting surface. So what I've done is define this new highly heterogeneous surface. So it's a bit more of an idealized case, but we're using that grid cell I showed you previously. So we're evenly dividing the grid cell between urban, lake, grass, and irrigated cropland, and initializing plumes over those. If you want to talk about the CLUB MF details, I'm totally happy to. Ultimately, the important points to know are we have 25 updraft plumes. We're going to basically spread those evenly across the surfaces, so about 6 plumes initialized over each of the patches. And we're using constant entrainment length. You probably don't need to worry about that, but if you are curious, we can talk about that too. What I also want to note is that averaging over 2 years worth of summer is probably masking some days that are more sensitive to the addition of heterogeneity than others. So what we're doing is kind of a first pass to understand some of the sensitivities. We're defining clear, cloudy, and rainy days. With the idea being that on clear days, maybe there's less synoptic forcing, the influence of heterogeneity could be larger. It could be fairly large on cloudy days as well, but on rainy days, we would expect that maybe there's larger synoptic forcing. The rain is kind of acting to homogenize all the surfaces a little bit more than if it's clear. So we might expect to see more limited heterogeneity impacts there. So if we move into some of our initial results, I just kind of want to orient you to some of these plots. So here we're looking at mean vertical profiles in the atmosphere of updraft plume properties. So this is all 25 updraft plumes averaged together. In the homogeneous case in gray, which is kind of our control, and in the heterogeneous case in pink, we're looking at 2 periods, 3 a.m., so middle of the night, 3 p.m., middle of the afternoon. And then we're looking at updraft temperature and updraft moisture. So if I can get this pointer to work. Oh, that's fine. Hey, awesome. So what's interesting to note, I think, is that if we compare just 3 a.m. and 3 p.m., there's much more of an impact of heterogeneity happening overnight than is happening during the day. It's actually not necessarily what you might expect to see. I would say based on observations, we tend to see that difference in convection happening during the day. What's happening at night is actually really interesting though, because we're basing it not on grid mean values, but on individual tiles. So in a grid mean sense, overnight, a lot of the convection tends to shut off and you're not necessarily initializing those club MF plumes because they're based on grid mean buoyancy. But if I'm initializing them based on individual tiles, what happens is that the lake patch actually stays a little bit warmer and a little bit wetter than the grid mean overnight. So the lake patch remains active even if the grid mean flux might have turned off. There's less of an impact during the day, but you can still see that the updraft temperatures in the heterogeneous case are warmer than the homogeneous case. And there's maybe a bit of a sign that the updraft plumes are wetter near the surface as well. So that's just for clear days. Next, if we look at cloudy days and rainy days, again, I think there's some kind of unique differences, but overall the story is fairly consistent. On all days, we see that the updraft temperature increases when you add in heterogeneity, more so at night than during the day. During the day, actually, on rainy days, what I think is kind of interesting is that there's almost no impact of heterogeneity. Oh, that's the next button. No impact of heterogeneity here, right? So those lines are pretty similar. In terms of moisture, maybe a slight increase, but again, not much of a signal on rainy days. So we're really looking at the cloudy and the clear days for when interesting things are happening. And as I mentioned before, with kind of the lake patch and what's happening overnight, one of the neat things about this framework is that we can isolate which plumes are being initialized over which surface. So what I've done here is just taken any plume that's initialized over the lake at 3 a.m. and any plume that's initialized over an urban area at 3 a.m. and just plotted those here. So what's interesting to see is that the heterogeneous signal overnight driven almost entirely by these lake plumes. During the day, it's a bit of a different story. What we see is actually kind of this tension between the lake plume being cooler, the urban plume being warmer, vice versa in the moisture amount. It's kind of acting to modulate where the heterogeneous mean case is falling, but they're kind of counteracting each other and acting as a balance. So even though the mean might not show a lot of change, you can imagine that the plumes that are initialized over one surface versus the other are pretty different. So one of my first questions was, does sensitivity to heterogeneity vary across days? Mostly I would say that yes, it does. Overnight, the heterogeneity leads to enhanced updraft temperature, regardless of what kind of day we're looking at. But overall, the updrafts are more sensitive on cloudy and clear days than we see on rainy days. But one thing to note is that thinking about what happens with these kind of idealized updraft plumes might not actually matter much to most of us in the real world. So what I wanted to look at was, are there differences in clouds or precipitation, something that's a little bit more tangible than just, are the updrafts warmer or not? So one of the interesting signals I think we see is in temperature. So these are diurnal cycles of 2-meter temperature on clear, cloudy, and rainy days. If it's put in like a bolder color, that's the day we're looking at. Homogeneous case and solid, heterogeneous case is dashed. So what's interesting to note kind of right off the bat is that in all 3 cases, we see that the overnight minimum temperature is actually decreased when we add in heterogeneity relative to homogeneous cases. And on clear and cloudy days, the maximum temperature is actually increased a bit too. So we're enhancing the total diurnal range of temperature when we add in heterogeneity in these cases. And one last big plot result is cloud liquid water path. So thinking about kind of how much cloud cover you have, how thick it is, and that can feed into the temperature results. What we see is when we compare the heterogeneous and homogeneous cases, which is in the red and blue plots on the right, the heterogeneity is acting to reduce the amount of cloud liquid water path we see relative to the homogeneous case. Even on clear days where you really don't have a lot of clouds, so they're clear, you do see a general decrease in cloud liquid water path. So it seems to be a pretty consistent result that adding in heterogeneity is leading to that reduction. So we do see enhanced nocturnal cooling near the surface in all cases of days, but it's strongest on rainy days in particular. Clear and cloudy days show a larger diurnal maximum temperature as well, which could be tied to that cloud liquid water path, also cloud fraction changes, which are impacting the total net incoming radiation at the surface. So just a few takeaways. One important point I think is thinking not about necessarily creating new parameterizations, but new linkages between them for how we can actually capture processes that are missing in the model. So here we're looking to capture land-atmosphere interactions that can occur below the 100-kilometer grid scale. And these mass flux plumes are a really important tool for doing that because they carry the signal of heterogeneity from the surface up through the vertical more efficiently than if we were to use something smaller like CLUB itself. As we look towards the future, we do need to validate this new scheme against observations. That's difficult to do in the current setup because I've defined this kind of highly heterogeneous surface, so totally different system in some ways. It's important to also note that we're exploring the impact of various club options. So this is actually a new development in the last few weeks. Adam Harrington's discovered that club has a double diffusion within it. So it's diffusing temperature and moisture in a way that isn't necessarily correct when you have mass flux on. So we'll rerun our simulations with that off. But the goal is really to use this as a way of representing those mesoscale secondary circulations directly. So if we have these mass flux plumes, we can kind of say, this is the updraft plume, here's the downdraft, and start capturing maybe connections between them to represent overturning circulations in the atmosphere. So with that, I will end. I'm happy to take questions.
Thanks, Meg. I've got one question to start things off. Sorry, actually, go ahead. Go ahead.
This is really cool, thank you. Just clarifying and then the actual question. So it looked like these were run at a site, right?
Yes,
Kind of?
you got idealized site.
Idealized site, but it's still like a single point as opposed to
Yes.
running full 3D cam. So could you then use this and force it with a bunch of different like towers or locations to isolate like where this actually matters? Like what sort of regions, like is it bigger in Southern Great Plains versus Seattle versus the Amazon versus the Sahara? Like where heterogeneity has a strong impact on what the atmosphere is doing?
That would be really cool. Yeah, I think, so there's a couple ways to do it. We could do like more single point simulations at those kind of tower sites and be like, hey, it matters. Which would be awesome if we have the forcing to do it. The other option is just running this globally.
Right.
So Adam Harrington, they're running, I know, Adam's running MF globally right now. I mean, it's really cool to see. Yeah, but it doesn't have this heterogeneity part. But yeah, I think that's the next step. It's just like, let's run it globally and see.
Very exciting,
Yeah.
thank you.
Yeah.
Related to running it globally, I was wondering, what's the performance hit when you turn this on?
Not much. I should have a better answer because I've been asked this before. But ultimately, when we're running it with MF, like we're already initializing those 25 updraft plumes, it's just passing like 3 extra things through the coupler. So there's no hit on the MF side of things. Yeah,
Makes sense.
which should be the more expensive part. Yeah, good question. I see, Gordon.
Yeah, Meg, great talk, thanks. Yeah, I want to go back to first slide you showed where you talked about the difference between WRF, LES, and SCAM, and you said SCAM wasn't showing the sensitivity that you see in the LES. And I was wondering, how much is that related to the different ways in which the vertical resolution of the models essentially? And maybe I don't know anything about WRF LES, but how is the land sort of represented in that? In contrast to SCAM, there's like this artificial boundary, at some, like 60-meter height or something like that.
Yeah.
And presumably the LES has a higher vertical resolution. Probably still has a boundary condition at the ground of fluxes.
Yeah.
But so the point is, does vertical resolution factor into these the impact of horizontal heterogeneity?
Yeah, so LES is definitely a higher vertical resolution. What I would say that in this case, I don't think that's the culprit. What's happening in LES is that because it's representing kind of these, hundreds of thousands of atmospheric columns that are talking to each other, what LES is doing is setting up those secondary circulations explicitly. So it's saying we're going to transport heat and moisture from this warm, dry area over to the wet one. And what it actually does is it acts to organize convection in the heterogeneous case. It does increase precipitation, but it's more that it's organized as a result of that resolution. We've done experiments where we do different vertical resolutions to some extent between like L32, L58 in CAM development. I wouldn't say there was a ton of difference. I think it's really more that explicit representation of secondary circulations that's happening in the LS. Yeah, that's a good question. Yeah.
I just want to check, do we have any questions online? Cool.
Okay, that's,
Actually, no, I don't need that.
I didn't see who was first. Oh, so I'll move first and then I'll do one.
Alright, I'm curious what the time stepping is. Like, is it all happening in the same time step, or like even within it, do you consider like, say, one tile is more unstable or has less inhibition, so you do that first and see what happens to the adjusted atmosphere for the rest of the tiles?
That's a more complicated way of doing it that I'm not doing. Yeah, I would say that the way I have it set up right now is that essentially at every time step, it's just going to grab whatever the land tiles are giving us, and it's going to do its MF plume initialization using those, information. But there's no consideration of like, oh, let's make sure we do the lake patch first before the urban patch or something like that. But that could be cool. Yeah. Well,
If you made the same plot with your new club MF results,
what would it look like?
All right, I made it with the fake surface and I wasn't like super thrilled. My guess is that it's gonna have a bit more of a vertical cohesive structure. It's probably not gonna show us kind of that overturning circulation that would give us the full picture we see in LES. Yeah, but at least there should be some more of a vertical signal than like lowest model level only. Yeah, but that's a good question. I think we should rerun it with kind of the real surface. But it's hard to get a signal in such a homogeneous light. Yeah. We have time.
We do.
Any speculation on what this would do to the diurnal cycle of CO2?
Sadly, no. I don't know a lot about the diurnal cycle of CO2, but I can imagine that if you're changing, maybe the temperature gradient plants are going to respond in a little bit more of a unique way. Maybe they're more stressed during the day. I don't know if you'd see a shift in timing, per se. Yeah, that's it.
Good, yeah, I think we have time for Josh online.
Sorry if I missed this, but do you actually provide spatial information for the subgrid tiles, or does that matter in your implementation?
It's a really good question. Sadly, no, I'm not providing spatial information, so we don't have that in CLM, so I haven't gone through the effort of kind of finding a way to figure out the spatial connection between these patches, but it is hugely important, right? You can imagine that if you have a warm patch that's like fully contiguous versus a cool patch that's fully contiguous, that secondary circulation would be stronger. If it's kind of scattered and spread out, you're not gonna get as much of a signal from that heterogeneity. So the length scale at which heterogeneity occurs is really important in reality, but difficult to capture in this particular framework.
Thank you.
Quick follow-on to that.
Sure.
But in Club NF, are they spatially explicit? So you couldn't in this way do it anyway, yeah.
Yeah, that's a good point. Yeah, they're both kind of like statistical, but not spatially explicit. Yeah, so we're consistent.
All right, thanks very much, Meg.
Thanks.
Next up we have Claire.
Awesome. All right, thanks. So today I'll be sharing some work, part of which I've presented before. So this conclusion that atmospheric modulation of ET depends on the climatological moisture regime is something I've found for a while, so maybe presented to some of you before, but I think I can explain it better now. So maybe I should have framed it like why atmospheric modulation of ET depends on the climatological moisture regime. So the motivation for this topic is pretty simple. Evapotranspiration impacts climate, and climate impacts evapotranspiration. And in particular, a lot of the same atmospheric quantities that multiple studies have shown for a really long time can influence ET are also influenced by ET. So we know that changing land evapotranspiration can drive local, regional, and remote influences on precipitation. Changing the land water flux also controls the relative humidity and temperature of near surface air, so directly controlling the BPD. And we also see cloud responses to changes in ET, which influence net radiation. So there's the potential for the atmospheric response to evapotranspiration to feedback on the land surface change itself. So I'm looking at how this land atmosphere feedback modulates changes in ET. And it turns out a lot of previous studies I think aren't really well designed to disentangle the influence of this land atmosphere feedback. So lots of studies look at ET in a land only framework, which no one would claim accounts for land atmosphere feedbacks, obviously. So that's fine. But I think coupled frameworks alone also can't disentangle the impact of land atmosphere feedbacks. So coupled frameworks quantify the net coupled response in evapotranspiration, but they don't allow us to disentangle how much this land atmosphere feedback is contributing to that overall net response. So on their own, neither land only frameworks nor coupled frameworks for thinking about land evapotranspiration can quantify the land atmosphere feedback. You really need a combination of these two perspectives. So we combined these two approaches so that we can isolate the impact of atmospheric feedbacks in modulating land evapotranspiration changes.
So specifically, we were using these two paired perturbed parameter ensembles. So we ran one where the atmosphere can respond to changes in the land surface, and we were just looking at biogeophysical feedback. So the atmospheric CO2 concentration is held fixed. And then another one where the atmosphere, we take the atmosphere from the default coupled simulation and use that as our external forcing for the land model. And we ran these one at a time simulations where we perturbed 18 land parameters to minimum and maximum values. I'm kind of like breezing through the details of what we did because some of you may be familiar with these results. And the fact that we used perturbed parameter ensembles kind of doesn't matter. Like we were using this data set as a tool to learn about land atmosphere feedbacks more than doing like a parameter estimation or uncertainty study. So basically we ran 36 different ensemble members where we were changing land evapotranspiration by like mucking with a bunch of assumptions about the land surface. But like critically, we were doing it in this paired experimental design so we could isolate the impact of atmospheric feedbacks. So as an example of doing this pairwise comparison, I want to start by looking at a single point. So I'm going to compare the land-only change in the latent heat flux at a point in the Amazon to the coupled change. So, okay, I'm going to try to use the pointer. Yeah, I'm not going to. So our null hypothesis is that atmospheric feedbacks don't do anything. So if that's the case, we'll have all of our points on this one-to-one line. And if atmospheric feedbacks are amplifying changes, will be in this like red regime, and if atmospheric feedbacks are dampening, would be in the blue regime. And so if we add our data where each point is this like paired ensemble member, see a couple of things. So first, all these points are off the one-to-one line. So like big picture takeaway is atmospheric feedbacks are doing something. They're also consistently in this dampening regime. So at this point in the Amazon, atmospheric feedbacks are consistently dampening changes in land evapotranspiration. And this is like pretty consistent across the whole parameter space we were sampling. So again, like not getting super into the weeds of what parameters we were changing, but it doesn't seem to matter much what process is driving the initial land-only change in evapotranspiration. The atmosphere is acting to modulate that change in a pretty consistent way. So specifically, for any change in land evapotranspiration, like say this is the Kmax change, it increases latent heat flux in the Amazon by 20 watts per meter squared. We're going to have about a 40% smaller change in a coupled context that we've just in like the land only framework. So this effect can be pretty big. And so far we've just been looking at this one point to kind of build intuition for what we're trying to analyze. But if we extend this analysis to all land when it's not snow covered, there's actually a lot of spatial variation in how atmospheric feedbacks are modulating changes in land evapotranspiration. So this is the same kind of color scheme in that places that are blue are places where the atmosphere is dampening changes in evapotranspiration, and red places have that atmosphere of the amplifying effect. And all these like stippled or striped regions indicate places where the atmospheric feedbacks aren't statistically significant. So these would be places where points are pretty close to the one-to-one line. So the slope isn't statistically significantly different from one. So to explain this spatial variation, I am going to take a couple of minutes to walk through the Boudico framework, which I imagine a lot of you are familiar with, but there are lots of variations on it. I kept this slide because I used it in my defense, and I thought it was very cool that the original like 1956 Boudico paper we get from the CIA because he was a Soviet scientist in the 1950s. So I figured this audience might appreciate that throwback as well. So yeah, there are lots of variations on the like Boudico framework. I'm sticking with the original 1956 kind of plot. So we have the aridity index on the x-axis and the evaporative index on the y-axis. And BGCWG frames there as being like two fundamental constraints on land evapotranspiration. There's a theoretical energy limit, which means all energy at the land surface is used for evaporating water. So if you're limited by energy, you fall along this line here. And then there's also a moisture limit. So you'd be along this line if all precipitation that falls at that place is evaporated. The meaning of these lines are switched in some like variations of this space, like if soil moisture is on the x-axis, but I'm sticking with the simple one. So if we plot all of the land grid cells from our reference coupled simulations in this BGCWG space, we see that transition from energy limited to moisture limited across this characteristic BGCWG curve, just like we'd expect. And just to note that since I'm using this old school aridity index, we should really think of points in the energy limited domain as being limited by like potential evapotranspiration rather than just by net radiation. So all these grid cells fall below the theoretical energy limit because evapotranspiration in an energy limited place isn't just limited by net radiation, it's also limited by like BPD and aerodynamic and evaporative resistance. So we should think of this part of this BGCWG space as being limited by like PET. So if we plot the influence of atmospheric feedbacks in this BGCWG space instead of looking at a map, there's this really clean separation between atmospheric feedbacks dampening in the energy limited domain and then either amplifying ET changes or having no impact once you move into the moisture limited space. And that transition between atmospheric feedbacks being dampening or amplifying occurs right along this inflection point in our BGCWG space. So this is where the new part starts. So why do we see this atmospheric, the influence of atmospheric feedbacks varying? Why do we see this dependence on the climatological moisture regime? So I'm going to build up a diagram for explaining this, where we start with our initial perturbation to the land surface, which is that we're changing something about how the land works so that we get an initial increase in evapotranspiration. That cools and moistens the boundary layer, so we have an increase in relative humidity. Almost all the maps I'll show are just based on like simple local linear regression of the coupled change to the land-only evapotranspiration perturbation, so like just focusing on the land to atmosphere impact. And so this increase in relative humidity and decrease in temperature decreases vapor pressure deficit, which decreases potential evapotranspiration. Potential evapotranspiration decreases everywhere in response to the initial increase in ET. And so this could have been driven by changes in like net radiation via clouds or BPD. It's mostly due to BPD. And that decrease in PET acts to dampen the initial change. So while potential evapotranspiration decreases everywhere, it only matters if you're in an energy limited place, because only energy limited places have ET fundamentally like controlled by potential evapotranspiration. So to illustrate this more clearly, I ran some additional simulations where I isolated how changes in atmospheric quantities impact land. So this is showing the results of simulations where I just decreased temperature by 1 degree in the like coupler forcing file at all points in time and space. And so this decreases potential evapotranspiration, but it only matters in the energy limited places. It doesn't matter much if you're in a moisture limited location, because in those places what really matters is precipitation. So we have to think about a different feedback as being important in a moisture limited regime. So in some regions, though not all, increasing ET can also feed back on evapotranspiration. This is the regional response of precipitation changes to changes in ET. And so if you're in a moisture limited place and precipitation in that place is also sensitive to the land water flux, then you can amplify your initial change in ET through soil moisture feedbacks. And again, we can visualize this more clearly by just isolating how ET responds to precipitation. So this is another like synthetic meteorology simulation where we just increase precipitation by 10% everywhere. And so this precipitation change really matters most when we're in these moisture limited places. So we identified like these two different mechanisms at play in different moisture regimes. And so I think like each individual arrow in this diagram is kind of obvious and like very well established by either prior work or kind of first principles, but we can learn something new by like coupling them all together to disentangle how a change in land evapotranspiration impacts the atmosphere, and that atmospheric response modulates the initial change. And I think in particular, this like energy limited feedback has been a little like underemphasized in prior work. A lot of people talk about precipitation, like soil moisture feedbacks with evapotranspiration, because that's something we can like disentangle easily from like observational studies or variability in the climate system. And I think this like VPD feedback on ET is a little less emphasized. So this is kind of a qualitative description of these two feedbacks. We also do this more quantitatively. So specifically, we did a linear decomposition to quantify how much different atmospheric variables contribute to this overall feedback. So as an example, to quantify the contribution from precipitation feedbacks, we start with the precipitation sensitivity to evapotranspiration, which we quantify with simple linear regression of the coupled atmospheric response to the land-only evapotranspiration change. We multiply that by the evapotranspiration sensitivity to precipitation, which we diagnose from these synthetic meteorology simulations. And that gives us the modulation by this ET precipitation feedback. And we did this for every month of the year. And then we repeat it for all of the variables that are passed from the atmosphere model to the land model and could therefore potentially have this modulating influence. And that like simple linear decomposition by month actually captures the spatial pattern pretty well, a lot better than I expected actually. And so our linear reconstruction captures like this emergent dependence on the climatological moisture regime. And it turns out we can mostly explain this just by feedbacks with temperature and precipitation. So there's some more interesting stuff happening in the tropics with specific humidity and in the high latitudes with like short wave and long wave radiation. But the like minimal information we need to capture this dependence on climatological moisture regime we can get just by looking at feedbacks between evapotranspiration and bottom of the atmosphere, air temperature, and evapotranspiration and precipitation. So in conclusion, the like main finding is that land atmosphere feedbacks dampen evapotranspiration changes in energy limited regions and amplify evapotranspiration changes in some moisture limited regions. We further show that we can explain this because in energy limited regions, we have this feedback driven by changes in potential evapotranspiration. And in moisture limited regions, we only get this feedback if you're in a moisture limited place where precipitation is sensitive to changes in evapotranspiration. So I was using perturbed parameter ensembles as a tool for disentangling these feedbacks. I think the fact that we get different answers in a coupled context than in a land-only context points to the need for doing model development or like some part of the model development cycle in a coupled context. So for folks trying to tune the land model, I guess it's kind of a philosophical question of like whether we should tune the land model to do well in the historical and a coupled context to account for like potential biases in the atmospheric model or not. But I personally think there's a value to doing some of this like tuning and benchmarking in a coupled context. And since we found this kind of emergent behavior of the atmosphere that I think is a lot more like generalizable from just the parameter uncertainty context, I think this means that if we're using like a land-only framework to assess how evapotranspiration responds to any land surface change, we're going to overestimate it in wet places and potentially underestimate it in some dry places where there's this strong coupling with precipitation. So yeah, would love to answer any questions.
Got time for a couple questions?
I'm curious, like for the land-only simulation, what meteorological forcing you use to force the land model?
So we took the coupler output from our like reference case, our default simulation, and used that as the forcing. So there are definitely biases in that, but it's like it should be really like apples to apples with the coupled simulation for that reason.
Abhishek, you can unmute and ask your question.
Yeah, very nice presentation and like your work. I just have a question. Are you able to hear me?
Yes.
I have a question that you are running this perturbations, the ensembles. So can you tell me just how is the like what's the means how you are creating the perturbations? What's the scientific basis of creating the perturbations? Means we know that we can create the perturbations by estimating it, but is there any physics behind creating the perturbations? Because that is very important.
Yeah. So we just developed this ensemble to choose parameters that we, based on other work, would have a big impact on the atmosphere. So they're all parameters in the land model that were perturbed to kind of plausible minimum and maximum values. Sometimes those ranges were based on observational data, sometimes it was kind of developed by the land model working group. So they're definitely like extreme perturbations to the land surface, but the idea is it kind of captures the range of uncertainty. And then I think, yeah, so that's the uncertainty angle, but then we used it as just a way of changing evapotranspiration from the land surface so we can like learn something that we could apply to other contexts like land surface changes or like CO2, plant responses to CO2. I think we have the same dynamic.
Okay, means basically you are like taking into account the observational error and then creating the perturbations of that variable, and only the land surface state parameters are being perturbed, or even the atmospheric forcings are perturbed?
Yeah, great question. So yeah, we're only changing land parameters and then the atmospheric like variables, but not parameters, could respond to that in the coupled case, but we're only changing assumptions about the land.
Okay, thank you so much.
Yeah, thanks.
All right, thank you.
Right.
Start with Ben BGCWG. We just shuffle everyone's presentation.
Just draw that out. Yeah, so today, my name is Ben BGCWG. I'm working with Abby Swan in her lab group. And yeah, today I want to talk about the global hydrologic response to land evapotranspiration-driven warming. So we know that the hydraulic cycle amplifies with radiatively driven warming. This has been known for a while, and it's pretty well accepted. So on the right, I'm showing a plot from the kind of seminal Heldon-Soden paper from 2006, which shows the change in surface temperature on the x-axis and the change in precipitation on the y-axis for a set of coupled simulations that are forced with CO2. And you can see that precipitation is increasing at approximately 2% per Kelvin. And that's pretty robust among kind of these models, and it's been again like well accepted in kind of the atmospheric sciences community. And in this paper, they the authors propose kind of this simple scaling for the change in precipitation minus evaporation, which kind of relates it to a change in surface temperature. And basically it assumes that like it's kind of a thermodynamic scaling that takes into account increase in moisture in the troposphere and also kind of the general circulation remaining relatively constant. And since then, there have been other papers that have extended this scaling to better represent that zonal pattern of P minus E. I've included kind of 3 papers here which do that. Essentially, this includes kind of adding terms related to like gradients in surface temperature or relative humidity, which improves the kind of fidelity of the P minus E pattern in the zonal mean. But what's interesting for kind of me is whether this hydrologic response kind of remains the same when you're thinking about land ET-driven warming, because in all these cases, it's been used to describe a kind of hydrologic response to, again, like CO2 forced warming. But in fact, we do know that suppressing evapotranspiration alters the global hydrologic cycle. So Mercer-Legou ran idealized simulations with very large magnitude ET changes. And so in the upper right, you can see that's the change in latent heat flux. So you can see like incredibly significant reductions in ET over land. And these kind of provide these like 2 big end members and that show that you have surface warming when you suppress ET. There's also this shortwave cloud response, which tends to amplify the warming. And then for kind of water vapor, the column water vapor and the residence time of water vapor tends to increase in the atmosphere with these large magnitude ET forcings. And so related to this, so we have these 2 big end members, and what I'm interested in here, so first looking at whether kind of those radiative-driven scalings are the same, and also whether these processes from these end member experiments hold across a range of smaller ET perturbations. And so to do this, I'm leveraging Claire's couple of PPE, which she really nicely explained, and using this to examine small evapotranspiration perturbations. And since I'm thinking about warming, I think it's important to note that these surface temperature changes are primarily driven by ET and not surface albedo change. And so on the right-hand side, I'm showing kind of the zonal mean over land of the percent change, kind of the spread for the PPE, where the red line is albedo change and the blue dashed line is ET change. And you can see that the ET change is significantly greater than albedo. And then I also have kind of maps of change here. And you can see, again, like over land, the percent change, range of percent change in ET is significantly greater than the range of percent change in surface albedo. And kind of we've come to view this as an emergent feature of the PPE, where kind of the parameters we've changed essentially kind of amplify the fact that there's greater parametric uncertainty in representing ET over representing albedo in these simulations. So first, this is kind of very intuitive, but the surface temperature and ET are negatively correlated over land for across the ensemble members. And so this is, ET and surface change in surface temperature for the PPE. Again, there's a negative correlation. This makes sense. But again, it's very different than when we look at CO2 force simulations. So here I'm showing in the pink squares the basically CO2 force simulations from CNIP 6 with CESM at 1/2, 2 times, and 4 times CO2. And that has a positive correlation. And so the way to understand this is that in kind of for the PPE, the change in ET is driving the surface temperature change, whereas in these CO2 force simulations, the ET is responding to the surface temperature change. And I'll be reiterating this throughout my talk. But over the ocean, I guess I just wanted to show this as well. In both cases, in both the PPE and the CO2 force simulations, you have this positive correlation where in both cases, ET is responding to this change in surface temperature as opposed to driving it. And then again, showing kind of a linear regression of the change in surface temperature and the change in ET, kind of that pops, the land-ocean contrast pops out, where you have, again, that negative relationship or inverse relationship over land and the positive relationship over the ocean. So I just also wanted to kind of illustrate those land-ocean contrasts by showing this kind of 1-to-1 plot where you have change in ET for the ocean on the y-axis and for the land on the x-axis. And so as expected, for the PPE, you have this, again, negative correlation where when you increase ET over the land, again, you're gonna have a surface cooling, which is associated with a decrease in ocean ET. Whereas when you decrease ET over the land, you're gonna have surface warming, which increases ET over the ocean. When we look at the CO2 force simulations, again, that's drastically different because for the ocean and the land, they're both responding, or ET is responding to a surface temperature change and not driving in any sense. So now synthesizing kind of those two, kind of that understanding of how ET and temperature are related, I want to now focus on kind of the precipitation response specifically. So here I'm showing the change in precipitation over land as a function of the change in surface temperature, where the shading is representative of that change in ET. So kind of what I've been showing earlier is that gradient in color, which you can see you're looking in temperature space, where cooler, bluer colors are associated with decreases in temperature, and warmer colors are associated with kind of, again, like reduced ET and increased temperature. As you can see, there's a negative relationship between precipitation and temperature, which is, again, like in line with that negative relationship or inverse relationship between ET and temperature. And what's important, again, is that it's completely different for the CO2 force simulations. And looking at, again, those color gradients to start, they're opposite, which I was showing in the earlier scatter plots, where when you have CO2-driven rate of warming, you have an increase in evapotranspiration associated with that increase in temperature, and also an increase in precipitation. Yeah, increase in precipitation. Whereas when you have a decrease in temperature and you have a decrease in temperature and a decrease in evapotranspiration, again, because those are coupled and responding with each other in the CO2 force simulations. I think I just want to pause here to note that, like, again, in the kind of atmospheric sciences community, that the relationship in the CO2 force simulations are, again, like, not new. It's pretty well expected, and it's well known and expected. However, when you have those evapotranspiration-driven temperature changes, you have the opposite relationship. And so when you have warming in the due to evapotranspiration, you have a decrease in precipitation, which is very different in a completely different regime than in the CO2 forced simulations. I also wanted to kind of touch and come back to that shortwave cloud response and to see whether you have that same response in kind of that middle space between the two end members that was in kind of Marissa's work, and we do still see that. So here I'm plotting the land change in evapotranspiration and the change in downwelling shortwave cloudy radiation at the surface. And so here, again, it's pretty evident that when you have an increase in evapotranspiration over land, you have a decrease in that downwelling shortwave cloudy radiation due to increased clouds, and vice versa when you're decreasing evapotranspiration, suggesting that this is, again, still even in these like small range of ET perturbations, still an important factor for kind of near surface temperature change. And then I also kind of threw up the changes for the CNIP6 like CO2 force simulations, and again, it's the opposite because you don't have that coupling or that kind of ET-driven temperature response. And then I have a map of, again, this is not the shortwave cloudy downwelling radiation, but just cloud fraction across the PPE ensemble. And again, this just kind of illustrates again that land-ocean contrast when you have ET perturbations, and you can see that over land, low cloud fraction and ET are positively correlated and have a positive relationship, whereas over the ocean you have kind of the opposite happening. And again, this just suggests that that shortwave cloud response is still important when you have like small ET perturbations between those two big end members, and that kind of mechanism still exists and is still important. So so that's kind of the main point. And I just want to go over, again, these take-home points. For the PPE, basically decreasing ET causes an increase in temperature. Again, this is because that's how we're changing temperature in these simulations, and that's why you're having a temperature change. Whereas in these CO2 forced experiments, the ET is changing with temperature. You're having a radiatively driven temperature change over the surface, and ET is responding to that. Over the ocean, for both the PPE and the CO2 force simulations, again, you have ET responding with temperature because over the ocean, you're not have the PPE is not changing parameters of the ocean, and it's also like not moisture limited. So the relationship is it the same, and it's positive. And then, kind of this is I think the main point I'm trying to try to get across is that you have these opposite precipitation responses with the same type of temperature perturbation. So for the PPE, when your precipitation decreases with increasing temperature, whereas for the CO2 force simulations, precipitation is increasing with temperature increase. And again, like I'm going back to like the earlier points I was talking about, like Held and Soden, that's again, like this is completely different regimes when you have evapotranspiration driven surface warming versus CO2 forced surface warming. And I'm not suggesting that like we should need to develop necessarily like a new temperature scaling for precipitation, but I do think that it's like just important to note that when you have these land processes that are affecting evapotranspiration, you can have a completely different hydrologic response to warming. I think that's kind of, the main point here. And then additionally, again, the temperature is like response is amplified over land from that shortwave cloud feedback, which is important for those kind of, when you have smaller ET perturbations, you still have this important mechanism for amplifying surface temperature change. So that's kind of the main points from my talk. But I did quickly want to include some extra results that are very unrelated, but I think a little bit curious, related to like fixing vapor pressure deficit. This was I was doing this in the fall, and I thought this was the crowd to like show this to. So we were fixing vapor pressure deficit near zero, and we found that the Amazon basically dies off, creates a new vegetation state, and the vegetation doesn't grow back, which we thought was just fun and a little bit interesting. So here I'm showing basically total mean change in LAI and total mean change in water stress. You can see that there's this like die-off of tropical rainforests in the first like 5 years, which is likely due to that increase in water stress. But even when that water stress alleviates, you still have vegetation not growing back. And it's interesting and kind of fun to look at. But that's all I have. I'll go back to our take-home points.
Got about 5 minutes for questions.
Yeah, that was great, thank you. I'm pretty familiar with CO2 radiative perturbations. We burn fossil fuels, more CO2. Yeah. What's an example of like a ET perturbation in the realm of global change or climate variability?
Yeah, I think probably like related to if you're growing more trees, you're gonna have an increase in ET. Land use changes could affect ET as well. I think change in vegetation cover would probably be the first thing I think of. But yeah.
Great, thanks.
This is really neat. Have you thought about doing another ensemble of PPE at a different CO2 concentration? Would you get a different answer?
I think that's been discussed, and I think it would be definitely very like interesting and valuable. I don't know if anything's in the works, but it's definitely like something that has come up in conversations. So yeah.
You showed many maps for the PPE runs. Wonder if you looked at maps for the CO2 ones and like what the spatial heterogeneity might be there, because it seems like maybe some of what you're talking about with the PPE runs might be applicable in like say moisture limited regions, even in the CO2 forcing.
Yeah.
So I'm curious what your thoughts are. If you
Yeah. I'm in the process of adding more like CM6 kind of analysis, and I definitely want to kind of continue to kind of examining that. I think different like moisture percentage limited regimes, looking at that, how that changes, I think would be definitely interesting. And I focused most of this solely on just like global mean averages, so I think increasing kind of the spatial analysis would be really insightful in that sense.
Related to what he was suggesting, I wonder if you did like an increasing CO2 experiment, but only the radiation felt the CO2 and not the plants. Because I think in the CMIP runs with increased CO2, the plants are seeing the increased CO2.
Yeah.
So it's not just the temperature effect that they're getting. It might be interesting to see where it lies on those
Yeah,
plots.
we probably could do that with six runs with like the BGC versus RAD.
That'd just be one couple run instead of
But yeah,
a PPE worth.
right.
We have a pending proposal to do it at higher CO2, but NSF has no budget, so.
So-
Tell them to, well, I have a proposal pending at NSF to do exactly what you all are talking, well, at least with higher CO2.
The PPE runs, does the global mean moisture change?
Yeah, so I was looking at, like the total column water vapor like increases and in terms, like atmospheric moisture increases.
Averaged over both the ocean and land together, it increases.
I believe so, yeah. I have some plots, definitely over the ocean, due to the warming. And I think it, again, because the PPE is like in some cases ET is increasing and some, like, I think that relationship is still there, where like if you increase ET, or, I'm pretty sure that global atmospheric water vapor does increase when you have like,
Just your interesting point on the next slide. I think it's known, right, a known issue with CLM is that once the plants die, they never come back. So I think that's just what you're seeing. Unless, I don't think you're saying that they just wither away, but they're still barely there and they won't come back, which could be a different.
they're not like regrowing, is that?
Yeah, they're not regrowing, but I think if like vegetation carving is to zero, then it just can't regrow, so it's an unfortunate feature. Probably don't submit it to nature.
We made that one flat and we're like, we should probably move on to something else.
Yes.
Good, there's nothing else in the room or online, we can go ahead and move on. Thank you. Now it's your turn.
Just too excited. Last time I was here was 4 years ago. Hello, everyone. It's really great to be back. Thanks for all the previous speakers talking about the climate feedback and also the Amazon. So this presentation, I'm also presenting a new paper we just published last year. So it's also focused on the Amazonia, especially how the two factors like deforestation and also the CO2 physiology response to the increase in CO2, how these two factors, they can contribute to the future precipitation change. So the motivation of this work is because we have the CMIP6. CMIP6 already include the land use change, the deforestation role. The CMIP6 already include experiments like C4MIP, which incorporates the physiology response in this set. So the motivation is here, we are doing like multi-MIPS comparisons because we use the C4MIP, we use the LUMIP, and also we use the scenario MIP. So we combine these different MIPS together. For each MIP, we use like consistently 8 models from different institutions, trying to figure out the primary drivers of future meteorological drought in Amazonia. So I'm showing you this picture from my collaborator. This is the deforestation in the southeast Amazonia, which is, the place is called Mato Grosso, which is in the critical zone from the forest conversion into some savannas, which also suffer from the land use change like deforestation. So for the map on the right bottom is is from the IPCC reports, which identifies future drought hotspots identified by these different models. So you can see Amazonia would be one of the most striking hotspot, which could experience like future drought. So I'm curious about because people always talk about deforestation, we always talk about the how CO2 increased greenhouse gas can influence the drought in the Amazonia. So by considering the deforestation, we additionally consider like let's say if we success avoiding the deforestation in the Amazonia, right? So the increase in CO2 or AKA CO2 fertilization will also cause the stomata to respond to this. So what is the contribution of that process? So here I'm just showing a recent review, from the carbon cycle community. So they're trying to integrate different evidence from the observations or from theory and also the experiment, like phase experiments, to try to illustrate how the CO2 fertilization could have on the carbon cycle. Especially, it is in general consistent that they conclude that based on this evidence, the CO2 fertilization it's generally agreed that could have the positive influence to increase land carbon sink for the future. But also, we noted they mentioned a little bit about the stomatal conductance response to the CO2 increase. So the general idea is like, these stomatal conductance will decline without like acclimation, which means like, if you continue increasing the CO2 and also the stomatal conductance will decline. So, from the ESM, from the Earth system model communities, these physiology models has long been developed over the past decades. So even for the CMIP6 models, if we go to revisit these physiology model, it mostly comes from those models from the 80s or 90s. So for this work, we are trying to really integrate the CMIP6 different sub-MIPs, like the C4 MIP. We are talking about the CO2, the radiative effects, and also there's a physiological effects. So I'm trying to use one of them, which is, okay, here we go. Yeah, so I'm really trying to use one of the simulation experiment, which is the CO2 physiology effect, which means the increase in CO2 only feeds the CO2 to the plant without any radiative impacts. So this is the CO2 fertilization can be captured by this set of simulations, but also the climate response can be captured from this set of simulations. Also, another experiment is the idealized deforestation experiment. This is the Dave's paper describing how the deforestation has been performed in this experiment. So basically, for these 8 models, we are trying to in the annual time scale, we're trying to isolate if there's any climate sensitivity to the interannual change in the CO2 concentrations in the atmosphere, and also if there's any climate sensitivity in response to the interannual change in the deforestation, especially in the Amazonia. So you can see from the very left column, so actually each point indicates 1 year from the previous transient simulations from those models. And is an average across the 8 models. So in general, you can see the CO2 physiology effects has like negative impacts to the precipitation in the Amazonia, and also the deforestation level to the precipitation. So what is interesting here is like we found like in the annually these models show like a transient, very rapid response to the CO2 physiology and also to the deforestation level. And also you can see on the right actually shows the precipitation sensitivity in response to every 100 ppm CO2 increase in the Amazon, shown on the right top. And also on the right bottom is the precipitation response to every 10% deforestation across the whole basin. And especially interesting for the pattern of the deforestation, because like there's recent Nature paper, claimed the tipping potential in the Amazonia. So they also use the moisture tracking tools to show that the forest, the moisture tracking, the moisture provided by the forest in the Amazonia actually will have hydrologic impacts to the south, to the whole west in other countries in addition to Brazil, because you can see the CMIP6 models here, also the precipitation decline a lot, especially to the west of the Amazonia, which is not only the Brazil, but also the all the other countries like Peru, like other Colombia, these countries, they will also suffer from these deforestation impacts. So the idea is like, because we have the transient climate sensitivity, so we can try to combine this sensitivity combined with the future CO2 increase, combined with the future deforestation levels. So these bars actually shows for different future scenarios, like from SSP 1 to SSP 5, you can expect like things are getting worse and worse from the SSP 1 to SSP 5, right? And also show the increased CO2, show the deforestation level in the Amazon basin. So if we multiply the climate sensitivity, from the loom MIP from the C4 MIP with the CO2 change and deforestation level here, so we can try to estimate these the contributions of these two factors, how they contribute to the actual SSP simulations in the future, right? So you can see the BGC and deforestation, they combine totally, despite of different future scenarios, our estimate shows like, at least 40% of future precipitation decline from the SSP scenarios can be attributed to the CO2 physiology and also the deforestation. And especially if you check, compare the BGC and also the deforestation, so you will see actually the CO2 physiology contributes a lot compared to the deforestation level. So which means like, we want to give some implication for the natural climate solutions, like, if even we stop the deforestation right now, the continued CO2 increase, caused by like fossil fuel emissions will continue to influence the precipitation and also cause the future meteorological drought in the Amazonia. And also we also do some like similar attribution for the relative humidity. You can see the relative humidity is also pretty big, especially 43% of future decline in the relative humidity in the Amazonia can be attributed to the CO2 physiology. And also the warming is kind of like, their combined is like 11% contributions, which is also kind of like consistent with Claire's paper before on the transient climate sensitivity contribution from the physiology experiment. So is this rainfall decline really water stress for the Amazonia, right? So this could be a really important question. So I believe if you check Abby's paper, makes previous paper. So for our current understanding using these Earth system model actually shows due to the physiology impacts, the runoff of the soil moisture actually will increase in response to the surface, in response to this physiology or CO2 fertilization, right? But I would say it's still hard to say because these are just the model simulations. I'm going to show you some evidence here. For example, this is my previous work showing specifically to put the satellite data, the biomass, onto the climate space. On the y-axis is the temperature, x-axis is the precipitation. And also I calculate, for different precipitation range, how the carbon responds to the precipitation, how the carbon responds to the temperature. So you can see the precipitation actually has pretty positive, the carbon has responsibly positive to the precipitation. So, and also the Amazonia, the climatology corresponds to a pretty sensitive of carbon to the precipitation. So if you experience of course, this is a spatial gradient. So which means if you experience like a declined precipitation, so the current spatial gradient will indicate there's a declined carbon storage from the forest, right? It doesn't matter how the soil moisture change, but also I would say we do not have very reliable soil moisture and also runoff data, especially in the tropics. And also another reason is like the current CMIP6 model, they did not do a really good job in representing all these like disturbances like fire, age effects, and extreme drought. So I like to highlight how the knowledge gap. So because we just talked about the forest cover, the vegetation cover change. From the model's perspective, we see a declined forest cover, the ET will decline, right? So I'm highlighting Paulo's earlier paper here. So he has kind of like monitoring the ET and also the NE in both like a degradation site and also a nearby intact forest site. So if you see from the year 2017, so you can see even the degradation site absolutely has a less forest cover compared to the intact site. So if you see the ET change, So actually the observations indicate there's a higher ET in the low forest cover site. And in this paper, he explained that probably because after the fire at this site, there are some post species change. For example, the after fire species, they could consume a lot of water and also to facilitate their regrowth. So these processes could be very different from if we are using the current Earth system model to do that. So which is can be really very different. And I like to very briefly highlight our the observations. Sometimes the model calibration parameter estimation really relies on the observational network. So for example, the SAPFlexNet provide the SAP flow, transpiration, and also these international soil moisture network. You can see actually in the tropics, the data is pretty limited. So some of you may heard about the NASA Above Field campaign. So for the next 10 years, right? So what these campaigns should go. So I'm kind of like co-lead working group in this scoping study. So the Pangea is also currently funded like a scoping study from NASA, but it's not guaranteed because it's competing with another scoping study focusing on the arid ecosystem. So this Pangea mainly focused on the tropical ecosystem, trying to really push the boundary of increasing the observations to increasing the application of NASA data into the tropics. And for this year's is in the phase of scoping like into a white paper. So next year, so this Pangea tropical study will compete with another dry ecosystem area to see who is going to be the next above for the next decade. So I would say this also provides a good opportunity for the modeling group. We can definitely use your expertise, especially if you feel like in the tropical ecosystem there are any observational need, and also to we can how we can use these observations to fill the gap, especially focusing on the climate feedback and also the interaction working group. Feel free to scan this code, to fill a form to stay in touch. So I would say this would be a really good opportunity. So yeah, I'll stop here.
5 minutes for questions again, and then we'll go into general discussion.
Is there anything online?
So you've done some really nice job taking existing climate model simulations and trying to learn what you can from them about deforestation and plant responses to CO2. Do you have suggestions for us about what kind of experiments would do a better job at that?
Yeah, exactly. That's really a good question. Actually, I just submitted a new proposal with Paulo. We are trying to increase the sap flow measurement and also soil moisture in his site in the Amazonia. I think one way to do that, because like we are talking a lot about the evapotranspiration, right? But if we are going to partition this evapotranspiration to transpiration, the soil evaporation, we actually, I would say, we will see a lot of uncertainties. We are kind of like clear about the general percent, for example, 6% or 7% of transpiration compared to the total evapotranspiration. But we are not so sure about how the temporal dynamics of that. This will directly influence, for example, if you have a vegetation, how the coupling strands would come from that. Also, relating to the carbon flux, it's super important to, not only limit our scope to precipitation or temperature. We really need to like a really good for high frequency soil moisture data, like daily, hourly, to see if how this soil moisture could control the carbon flux. So then we can isolate this from, for example, the BPD, the precipitation, all kinds of like meteorological conditions. I think these are, like two exciting directions I'm heading to. But also, I will also try to propagate, to persuade people to more integrate these network data, trying to improve. And also I believe for CSM, the plant hydrological scheme, like Daniel, you can definitely work on that, especially how we can estimate, like you showed for your slides, we have, even the parameters have a lot of uncertainties, as to cause the carbon, right? So I think these processes, we definitely can work on to improve for example, estimate global parameter data set using all the available observations. But it takes time, right? So. Oh, Dave and Claire.
I was curious if you had any intuition for whether plant community composition shifts in response to precipitation changes would make it lead to a bigger contribution from plant responses to the overall effect, or if it would go the other way.
You mean the species, specific species,
Yeah,
how that influence the climate or?
Yeah, it rains less and then you have trees that use less water or something like that.
Yeah.
Not fully thought
It-
through.
it-
I was just curious what you thought.
Yeah, it's super important, right? So I work with some people using remote sensing to focus on the species change, but it turns out it's kind of beyond their capability to see how this feedback, because basically here we are using the Earth system models to do that. Of course, you can use some high resolution, regional model or some models to do that, but it's really hard. Even if you are using, I heard from people using WRF with coupled with CTSM, coupled with some no IMP models. They're saying the surface flux response to vegetation change is not realistic. The albedo response could be in the opposite directions. But who is going to deal with that? Because they cannot use this existing model to publish papers, right? Because the model is not that good. And I would say it's definitely challenging because you need people both work on how realistic of these scenarios, but also you need people who are capable of changing the models, especially the codes to perform the simulations. It sounds a lot, right? To either integrate observations to do an analysis and also to change the model to make it reasonable, right? I did it when I was a PhD trying to put the satellite leaf air index into an Earth system model, which cost a lot of time. But still, but I guess because this is difficult, so I would say it could also be a good opportunity to have some breakout results, right? So.
I'm just trying to understand the result you showed from the Palo paper. So it was a degraded site compared to an intact site.
Intact site, yeah.
And nearby, very nearby, so they're
Very
the
nearby.
same.
It's very nearby.
And so it's not the same as deforestation, but it's.
Yeah, for the degradation site, actually, maybe starting 24, they are starting to burn the site. So it's they kind of burn it every year, and also for another site, they burn it every 3 years. So after 2012 or 2014, they just stopped the burning. So that site, definitely has low forest cover, but can be there's some vegetation recovery from the disturbances. But the intact forest is very close, has never been perturbed. Yeah.
Is this the Fazenda Tambora site?
Yeah, the Tango IPM station, yeah.
So do you feel like it's, I mean, we don't have, so CLM, I think, and most other models are showing a decrease in ET, right? And
Yes.
And so are you trying to argue that maybe it shouldn't, or are you just saying there's uncertainty, or what exactly is your?
Yeah, we are arguing this in a recently submitted proposal. So trying to increase the observation there. So to measure the sap flow, to measure the soil moisture, and because for this site there are existing eddy covariant flux observation there. So if we believe if we do the partition, we know the upscaled sap flow to transpiration. If we know the soil moisture, we can understand better about how the these difference, the difference in the vegetative composition can influence. For example, for the degraded site and also the intact site, we can measure exactly the same two species for the sap flow to see if they are consistent with each other, right? So if they're consistent, the short vegetation from the degraded site could have higher evapotranspiration. That's kind of like an inference, right? Also assumption, but only if we have the observations, to more than, eddy covariance flux.
So please feel free to keep asking questions of Yue, but we're in sort of our general discussion period until 2:50 p.m. Mountain. So also please feel free to ask questions of the other speakers from this session so far, or just general discussion inspired by the presentation.
People back up on the screen.
Yeah, can you do that from your end? Put the online attendees back on? Yeah.
Question for Team UW. You've made a compelling case for coupled model PPE, both their use and learning things about coupled model, but then also like your suggestion of coupling, like actually evaluating PPE more for calibration. It kind of terrifies me, like how quickly we'll blow through our allocation. And maybe it's mostly just an initialization problem. Like we've been able to do so much with the PPE because it's a sparse grid and it's land only. So you can do a ton of simulations for relatively cheap. Aside from being like, hey, like this matters, we should really pay attention to it. Like, have you gone and like, do you have any idea what it would cost? Like, what should I be asking Dave for in our next CSL allocation?
You want the good news answer first or the less good news? Yeah, go to the clarity answer first.
Well, I think a good news answer is I think we could apply some of the relationships we learn from kind of this minimal set to kind of guess how a coupled answer might be different, which kind of goes against what I said a few moments ago. But I mean, in places where there's this emergent linear relationship between a land only and coupled case, if the coupled case is different but it's predictable from a land. If you get all the information you need from a land-only context, you could maybe have some kind of correction factor that could deal with it.
Yeah, if you're wrong in all the wet places, you could just correct all of your answers in the wet places somehow without running them coupled. If we could try it. So basically we run one PPE, hopefully we'll run one at higher CO2, and maybe we can learn enough about some of the things that need to get corrected that you don't have to keep running them coupled.
Do you need the circulation feedback, so could you do scam stuff? Like single column?
Oh, single column, yeah. I mean, I think some of the I think you could do scam and learn a lot. Part of my study was, by doing the regression locally, we kind of discount all of the non-local effects to the greatest, or non-regional effects to the greatest extent possible. So I think you should be ready for some circulation surprises, but I think
I'll tell you what they are.
Yeah, I think you could do a lot of the most important stuff without accounting for circulation changes. Personally, that's a hypothesis more than something I've proven.
I want to talk about carbon in a minute, but if some of these other questions are related.
I think SCAM is very constrained in terms of precipitation by the moisture fluxes.
Oh,
So
right.
it might need to be a little fancier.
Yeah, kind of like what you do, regional,
Yeah, but that costs the
nudging.
same.
It costs the same.
Yeah, okay.
I think, right, you wouldn't have to do the full model, right?
Yeah.
I think
Yeah.
in this calibration cascade idea that we're trying to do for phase, it could be essentially an SP mode, right? You're prescribing the carbon state, you're prescribing the vegetation state, and you are trying to calibrate the fluxes with a perfect LAI. And then you have to keep those parameters kind of fixed or constrained when you move to try to calibrate the carbon part. So that seems like a strategy that wouldn't be that hard. And I think maybe you could also do it with, AMIP runs rather than the fully coupled. I know that you see some feedbacks in the fully coupled, but it's much, much easier in an AMIP configuration.
Yeah.
And
We
you have
did
some
slab
chances.
oceans.
Yeah. you could do slab oceans, but we had the problem with slab oceans, right, with present day.
there's challenges,
Anyway, there,
yeah.
so,
After having seen the results, I think it's mostly regional. Like, I think you could get a lot of the same thing.
so then it's more a question of what are your metrics?
Right.
And then you might actually ask, are you even looking at, I mean, if you talk to the land atmosphere coupling community, right, they're interested in a lot of like pretty detailed metrics about how soil moisture state can then influence the atmospheric profiles and feedbacks and a lot of your work so far has been on more mean state kind of stuff, is that's right? And so it wouldn't necessarily tickle them, you know, so it's just, it's, as with anything, it's like how far do you go down the path.
Kind of related to Will's question, you said you varied 18 parameters, right? Did you vary them per PFT one at a time, or does that add a layer of complexity and additional computational resources needed?
Yeah, it like pretty much mirrored like the CLM, like Daniel, Linnea, Katie, Dave, experimental design. So perturbing all like parameters, or many PFTs had different ranges, but went to the maximum and minimum of the range at the same time. Yeah.
So can you then disentangle like how much a tree is impacting versus how much a grass is impacting the feedback?
I think I could try to back it out, but not elegantly, like not unambiguously, based on what I've personally done.
I just wonder if that calls for more experiments.
Yeah.
I'm wondering if we can learn things about the coupled feedbacks on shorter time scales, so we don't have to spin the whole model up or run all of these simulations for the full time period. We can spin up our PPE and then just run shorter coupled experiments for a smaller ensemble and get some of the feedback. So do you have a sense for like how much you can learn on the short time scales about these feedbacks, and if that, propagates to your mean state feedbacks that you're finding?
Oh, that's a good question. How short? Like 3 years or like 5 days? I don't know, pressures of the same number, 3 years or 3 days. Huh?
On the order of years.
Yeah, I mean, I think you could, for trying to like frame this project in terms of other studies, like I think there's some like weather modeling, like studies on the timescale of years that can identify the same kinds of feedbacks, like especially in the wet regime, like the VPD feedback is pretty fast. I think it's more just like you can get the mean state change, you need to see like the whole seasonal cycle. But I think you could do it over a shorter time scale. I think for the precipitation feedbacks, it's harder to get like robust signals to see like if ET impacts precipitation. That's like a huge uncertainty, and like you need that for that amplifying feedback to happen. So I think that part, you need more of like internal variability ensemble or a bunch of years, but for the wet regime feedback, I think you get it pretty quickly and it's pretty robust. Yeah. Does that answer your question? Yeah. Okay.
All right, we're at Tintel, which is our break, if you have one last thing.
I was just gonna say it works differently for carbon. Claire didn't show this.
Oh, yeah.
But
Sorry.
it does work differently for GPP than it does for ET, but maybe still in a way that you could use it in a simple way. So basically, not all the parameters do the same thing. If parameters change the ratio of ET and GPP, they do it opposite to the other parameters. So you would need to categorize parameters in terms, like there's gonna be some things like that. But it still sort of fell into two groups, like things that affected water use efficiency, or the dry soil layer in dry places changed the relative amount of GPP to ET change, or the correlation between them, that changed the GPP response, and it only mattered in those kinds of places. Otherwise, GPP looked like the offline runs. So you'd still need correction factors that would be differently constructed.
Cool, thanks for the great discussion, y'all. We'll see you back here at 20 past the hour. Yeah, hope these discussions continue during break.
Thank you.
Can I just get a quick show of hands of who might want to go to dinner tomorrow, 5:30 under the sun?
Is it the cash only or not?
You can take cards.
Yeah, under.
Under takes cards, yeah.
Okay.
Good number, that's good enough, I think, thanks.
I moved on you, sorry.
You what?
I moved on you, I scored it twice.
I don't think it needs to be a hard number. That's a good start. Sam, were you still moderating?
No, I think it's.
You're gonna do it. Okay, great. Go, John. Go for it. Last jolt of sugar, I hope. Ready for some more talks.
Welcome back, everyone. I hope you already have a good bread, coffee, and get refreshed. So our second part is going to start. And our first speaker is Amy from Zoom or Google Meet. All right. Can you hear us, Zoom, Amy? If you can share your screen, I think it will be more flexible for you to control the
Cool. That sounds good. Let me find my screen. And then, can you guys see the slides?
Yeah, good.
Okay, great. Well, thanks. I'm Amy. I'm a grad student at UW. And today I'm going to talk about my work on understanding plant carbon-water trade-offs in the coupled system. And this is work done with a number of collaborators. And to start off, how do I move on? Okay, there we go. Okay, to start off, we know that plants have stomata on their leaves that can open and close, and plant processes like photosynthesis and transpiration are dependent on these valves since they allow water vapor to leave the plant for transpiration and the uptake of carbon dioxide for photosynthesis. So stomata essentially regulate the gas exchange between the leaf and atmosphere, and the relative rate of these processes can be related to water use efficiency, which is defined here. It essentially represents the carbon-water trade-off that, oh, is the slide not changing? Okay, I think there's a lag possibly at the slides. Okay, going back. So water use efficiency is essentially the carbon gain over water loss or photosynthesis over transpiration, or the carbon, sorry, tripping with the slides there. Okay, is it changing? Okay, sorry, technical difficulties on this end. So the carbon gain over water loss that plants make, and then it's closely linked to small conductance, which is the estimated rate of gas exchange based on small aperture. And small conductance is important to both plant processes like photosynthesis and transpiration, since it modulates that gas exchange, and thus can drive changes in both carbon and water fluxes. And these changes in fluxes can lead to impacts on the carbon-water cycle and thus climate. So these are important to both Earth's ecosystems and human populations. And we also know that plants can alter surface properties, so changes in surface properties can affect climate. And this plot from Liquid L 2019 shows that changes in evaporative resistance or an increase in evaporative resistance can increase surface temperature. So it's pretty important to understand plants. And then water use efficiency can be defined in a couple different ways. So the equation on top is the one I showed earlier, where I had technical difficulties at. And the bottom one here is another way to define water use efficiency, or intrinsic water use efficiency. And this is the term that we're changing when in our global scale simulations. So the one highlighted in green. So both equations are carbon gain over water loss. It's just a matter of whether or not it considers the environment or not. So how exactly are we perturbing intrinsic water use efficiency? We're perturbing it by modifying the Mellon slope parameter in the Mellon model for small conductance that's used in the land model. So that equation on the right there. So that term highlighted in green is the Mellon slope parameter, and that is what we are modifying to change the intrinsic water use efficiency. And if we look back at the intrinsic water use efficiency equation, we can see that the Mellon slope is inversely proportional to intrinsic water use efficiency. So there is uncertainty in intrinsic water use efficiency, and this stems from the Mellon slope parameter. This is a graph from Linnell 2015 plotting the estimated Mellon slope parameter on the y-axis and temperature on the x-axis. And each color is a different plant type. And what I really want to point out here is that you can see this huge range of possible metal slope values within the same plant type and across different plant types. And this leads to the large range in intrinsic water use efficiency values. And one melon slope value is typically used to represent each plant type in the land model. So for example, we'll take the broadleaf evergreen tropical trees. It may have a melon slope range of below 1.7 to a high of 9.11, but this default value of 4.45 is used to represent that whole range. So it's pretty simplified. So we know that intrinsic water use efficiency changes with the melon slope, and we have one value of the melon slope used in the land model. So if we change it, then intrinsic water use efficiency should change, and so what are the climate impacts of that? So we perturb the melon slope based on the 5th and 95th percentile of the Linnell 2015 data set I showed earlier. So here I have the scatter plot of all the melon slope values. We use each color, again, represents a plant functional type. So we're modifying the low and the high, and the low and the highs aren't equidistant from the default value. And then so this distribution of PFTs and melon slope values make up this spatial distribution of melon slope values. So this is the spatial distribution of the default melon slope values. And I want to point out here that the average melon slope value at each grid is not equal across the globe, it's different. So these are the questions we aim to answer today, and starting off with the first one. How does our choice of intrinsic water use efficiency impact photosynthesis? So we're going to walk through how a low and high perturbation would impact photosynthesis, starting off with the low intrinsic water use efficiency perturbation. So we would expect a decrease in photosynthesis if we look back or think about the intrinsic water use efficiency equation again, photosynthesis over small conductance. If we decrease intrinsic water use efficiency and we hold, and small conductance is constant, just to like have a conceptual understanding or expectation of what we would see, we would expect photosynthesis to decrease. And that is what we see in our results. So this is a spatial difference plot of the low intrinsic water use efficiency minus the default intrinsic water use efficiency simulation, and where brown represents a decrease in photosynthesis and green represents an increase in photosynthesis. We generally see decreases in photosynthesis across the globe. So the theory for this is that as we decrease intrinsic water use efficiency, we're forcing the plant to open their stomata and transpire more. And with greater transpiration rates, the plants are getting water stressed. So they decrease the number of leaves they want to support, and decrease in the total leaf area would decrease total photosynthesis. So now moving on to the high intrinsic water use efficiency perturbation, we would expect the opposite photosynthetic response to happen since we're perturbing it, intrinsic water use efficiency the opposite direction. So we expect to see a global map with a largely green color. And that's not what we see. Instead, we see a pretty regional response. So photosynthesis regionally varies with high intrinsic water use efficiency. So this brings me to the first take-home point I want to make, that our choice of intrinsic water use efficiency impacts photosynthesis. It does matter, and how intrinsic water use efficiency perturbation affects photosynthesis is more complicated than we initially thought. So now moving on to our second question. How much of the photosynthetic response can be attributed to the inclusion of a couple atmosphere and dynamic LAI? So the previous simulations I showed earlier all have the inclusion of a couple atmosphere and dynamic LAI. And we're going to call that the atmosphere plus leaf configuration. And I'm now going to introduce another configuration to answer the question where everything is fixed. So we have an uncoupled atmosphere and a fixed leaf area index. And we're going to call that the static case. I'm going to compare the two configurations for the different perturbations to see to answer the question. So previously, we saw that photosynthesis decreases for atmosphere plus leaf low intrinsic water use efficiency case. So our expectation or our null is that we see the same photosynthetic response for the static case. And that is what we see. We see the same spatial pattern, just a different magnitude. So photosynthesis decreases for both low intrinsic water use efficiency cases. Now moving on to the high intrinsic water use efficiency case, previously we saw a regionally sensitive response. So we expect that same regional sensitivity in the static case. And while we do see regional sensitivity for the static high intrinsic water use efficiency case, we see a different regional response. So in contrast to the low intrinsic water use efficiency cases where we saw a difference in magnitude but same spatial response, in the high intrinsic water use efficiency cases, we see similar scale but different spatial response. So to pull out where there's a photosynthetic sign response sign change, we drew a map here. So this is a photosynthesis sign change map for high intrinsic water use efficiency perturbations. And essentially where you see color is where there's a sign change between the atmosphere plus leaf and static case. And this brings us to our second take-home point that a coupled atmosphere enables the climate to respond differently. A spoiler alert, in our case, temperature increases. That's how climates respond differently. And we're going to explore two regions that are doing different things briefly. So the Boreal Canada and Amazon region. So in the Amazon, when we have a coupled atmosphere and dynamic leaf area, photosynthesis decreases. And when we have a static, okay, so everything's offline, photosynthesis increases, so the opposite happens. But in Boreal Canada, when both the atmosphere and leaf area are dynamic, photosynthesis increases, so that's opposite of the Amazon. And in the static case for Boreal Canada, photosynthesis decreases, which is also the opposite of what happens in the Amazon. So in both regions, we have a sign change between the static and atmosphere plus leaf case, but we have a different sign change response. But in both regions, we have the same temperature response. So in both cases, both regions, we saw an increase in temperature, but we have photosynthetic responses. So why is that the case? So I want to bring this little curve here. So this is a photosynthesis optimal curve inspired by Yamura et al. 2013, where we have photosynthetic rate on the y-axis and temperature on the x-axis. And the point where the plot peaks or the curve peaks is the thermal optimum for a plant's photosynthesis. And note that this curve differs for different plants. This is just a conceptual plot. So the plants in the Amazon might already be at the thermal optimum. So at that point there. So if we increase temperature, we're pushing plants in the Amazon past the thermal optimum for photosynthesis. While in Boreal Canada, the plants there might be at a lower point in the curve there. So if we increase temperature, we're pushing it towards the plants there towards the thermal optimum for photosynthesis. So plants in the Amazon Boreal Canada are at different points with respect to thermal optimum. So they respond differently to temperature changes. So our take-home point 3 is that photosynthetic response to increase in temperature is different in hot versus cold places. That background climate matters, and the atmospheric feedbacks are creating the temperature the differences for the different photosynthetic response. So now moving on to the final question we're addressing today. Does the photosynthetic response to intrinsic water use efficiency perturbation change with the increase of atmospheric carbon dioxide? So this is essentially the question again, but with a little schematic or figure where we're just showing that we double the amount of carbon dioxide in the air, and then we expect the small to close since there's a higher concentration of carbon dioxide, and that would increase. We would expect an increase in intrinsic water use efficiency due to the increase in atmospheric carbon dioxide. And what we see in our results is that increase in the atmospheric carbon dioxide increases photosynthesis as expected. So this is a spatial difference plot for photosynthesis. So we're not changing the intrinsic water use efficiency manually ourselves. And so for the two simulations of this difference plots, this difference plot is showing is that intrinsic water use efficiency is held as the default, and the only thing that that we're changing is the carbon dioxide concentration. We're doubling it. And so it's going across the board for increase in photosynthesis. We're going to break it down now and take a look at differences of differences to answer our original question of how intrinsic water use efficiency perturbation would affect photosynthesis at increased carbon dioxide. So this is the exact same plot I just had up in the previous slide, just minimized. So if we increase intrinsic water use efficiency, this would be the additional photosynthetic response that the intrinsic water use efficiency perturbation brings. So in other words, this is the change in photosynthetic response caused by the intrinsic water use efficiency perturbation at increased carbon dioxide. And if we add these two plots together, this gives us the overall response to intrinsic water use efficiency perturbation at increased carbon dioxide. So we're going to do the same for, we did the same for the low intrinsic water use efficiency perturbation. And we're going to pull up these two plots in the middle, in this middle column here, in the middle column next to each other. In the next slide, so for easier viewing. So in both of these plots, we can see that there are general responses to intrinsic water use efficiency perturbations. In the high intrinsic water use efficiency case, we see a largely increase in photosynthesis. The map is largely green. In the low intrinsic water use efficiency case, we see a largely brown plot or a decrease in photosynthesis. So why is this the case? So we're going to start off with, if we increase intrinsic water use efficiency, why is there generally more of an increase in photosynthetic response? And I know there's a lot of words on here, but we're going to walk through it. So going back to the equation of intrinsic water use efficiency, photosynthesis over small conductance, we're going to just say when we increase intrinsic water use efficiency and we assume small conductance is constant, so again, we're simplifying it for conceptual understanding, we expect photosynthesis to increase or give us a largely green plot, which is what we see. And if we do the same for the low intrinsic water use efficiency perturbation, where we decrease intrinsic water use efficiency and we hold small conductance or assume small conductance is constant for to gain a conceptual understanding or expectation, photosynthesis should decrease or give us a largely brown plot, which is also what we see. So we can say that the photosynthetic response to intrinsic water use efficiency perturbations at increased carbon dioxide are generally as expected, or it matches our expectation when we look at the equation for intrinsic water use efficiency. However, I do want to point out that both high and low intrinsic water use efficiency have regionally sensitive responses as well that account for around 10 to 20% of the overall photosynthetic response we see at the increased carbon dioxide. And we still want to explore why this is the case, which is next steps. So take-home point number 4, our final take-home point, is that intrinsic water use efficiency perturbation changes the photosynthetic response to increased carbon dioxide. So these are our take-home points, somewhat summarized. So our first take-home point is that our choice of intrinsic water use efficiency matters and affects the photosynthetic response we get, where we see a decrease, or if we decrease the intrinsic water use efficiency, we get a decrease in photosynthesis, but if we increase intrinsic water use efficiency, we get a regional response. And our take-home point 2 is that a coupled atmosphere can give us a different climate response. In our case, temperature increases, which affects photosynthesis, or what kind of photosynthetic response we get, which leads to take-home point number 3, that photosynthetic response to increased temperature depends on the background climate. And our final take-home point is that intrinsic water use efficiency perturbation changes the photosynthetic response to increased carbon dioxide. And I also want to end on the note that we mainly focus on the carbon part of the story. And the big picture question that we also want to answer for our next steps is that what does this mean for hydrological cycling and how does that impact events like floods and droughts? So, thank you. And I will leave the slides up here. And then I think if I go look at the Meet screen, the slides disappear, so I will let me know if there's any questions.
Thank you, Amy. Is there any question? Online or in the room?
Nothing online.
Okay, thank you. Oh.
Amy, you did a really nice job explaining a complicated story, and I'm trying to wrap my head around. I think like take-home 3 makes sense intuitively. I guess I'm curious if that pattern holds for other parts of the tropics. Like, do you see that downturn from warming related to changes in water use efficiency? And it seems like it's most robust in the Amazon, but I'm just curious.
Yeah.
Why it doesn't seem like it's happening as.
Yeah, it doesn't seem like maybe some parts in South Southeast Asia, but it's mainly just the Amazon and Central North America as well as the boreal regions. It's not as prominent in other tropics.
But do you have any idea why?
Oh yeah. I haven't explored or compared Southeast Asia yet, but that is a good next step to just clarify. Yeah.
Which one?
I guess a follow-up to that. I was almost gonna ask the opposite, which is for the boreal, I was noticing, at least in Canada, it really is kind of the tree line where that response is happening. It's not the whole Canadian boreal, it's kind of right there, which maybe kind of goes to sort of what you're saying, that might be the area where you would expect to be kind of temperature limited. So if you're increasing the temperature, those trees might get closer to their photosynthetic optimum if you're changing it. So maybe that's part of why there's some funny things. I have no idea what Siberia is doing, but for Canada, maybe that kind of makes sense. I don't know.
Yeah, definitely. It is a lot colder here, so I'm assuming like any energy, extra energy would make the plants happy and want to photosynthesize more.
Yeah, it's just interesting because the southern boreal's not really doing that, right? It's
That's true.
yeah.
I did only pull out the statistically if there's a difference, statistically significant difference in the photosynthetic response for both the static and atmosphere plus leaf case, if for this plot. So that it might have gotten filtered out in that sense, possibly.
Amy, that was a really wonderful talk, and I guess I just want to add that there is temperature acclimation in the model, and so it's a 10-day running mean temperature or that the plants, the photosynthesis responds to, and it does have constraints. I don't remember what the lower end is. It might be 0 Celsius, but the upper end I think is 30 degrees Celsius, and so then if the temperatures are getting warmer than that, it might put you into that space. So it might be also interesting just to look at to compare what those temperatures are and how much that might be contributing.
Yeah, that's good to know. Thank you. And then so would the plants acclimate after 10 days or?
It's the 10-day running mean temperature is what they acclimate to. And so then anything that is above or below that 10-day running mean temperature, the plants will adjust their response.
Okay, great. Thank you for bringing it up.
Okay, thank you, Amy. And if there is no more question, we can move to the next speaker, Maria.
Settles in on the desktop.
Oh yeah, I'll share my screen. So
It's really subtle.
maybe you can. Okay.
I've actually got so many windows open.
I know.
I can actually see the
It's like holding on restart. Yeah, go to view up there.
Oh yeah.
Okay, hi everyone, I'm Maria Salazar. I'm a second-year PhD student at the University of Michigan, working with Gretchen, Kepler Alex, and Allison Steiner. This is actually my first ever talk, so you might have to bear with me through some nerves. I'm going to be talking about how we can characterize El Niño Southern Oscillation teleconnection impacts on gross primary productivity across CMIP6 Earth system models. A mouthful. So to start off with some background, we see that variations in atmospheric CO2 growth rate are related to ENSO. You can see on the plot on the right, you see these spikes in atmospheric CO2 growth rate associated with the 1997 and 98 El Nino, and similarly for the 2015-2016 El Nino. So if we think that El Nino is causing these large CO2 growth rates, how do we think about what is the driving mechanism behind that? Well, we know that ENSO drives changes in global climate, resulting in a redistribution of temperature and precipitation, and those things then have a carry-on effect to terrestrial vegetation and the carbon cycle. So terrestrial photosynthesis represents a really huge exchange of carbon between the atmosphere and the biosphere, and so as it impacts radiation, temperature, precipitation, then goes on to impact the carbon cycle and more specifically the interannual variability of that. And you can see kind of in this plot on the, or schematic on the right, that the amount of CO2 in the atmosphere, one of the factors that controls how much remains there is this balance between the carbon uptake associated with GPP and the release back to the atmosphere from respiration and decomposition, et cetera. So these things, how those change interannually can drive changes in the atmospheric CO2 growth rate. So again, circling back, I'm looking at GPP as a metric for carbon uptake and focusing on these three climate variables, solar radiation, precipitation, and temperature, to see how that drives changes in GPP. So these kind of are my three shaping questions that we went about this work with, are how do CMIP6 Earth system models represent interannual variability and terrestrial productivity associated with ENSO? What climate variables drive these changes? And then also, are the differences between our models attributable to either those models' dynamics and how they're representing ENSO, or do they come from the land model response? So I was looking at fully coupled historical simulations from 1950 to 2014 using monthly output, these 10 CMIP6 Earth system models. For each model, I computed a model-specific Nino 3-4 index from area average sea surface temperatures in that top box. And that comes out looking like something on the bottom. That's CESM2's Nino 3-4 index. You can see if it's like above 1, that would be a strong El Nino. Below -1, that would be a strong La Nina. So getting into the plots, we're looking at here a linear regression of the Nino 3-4 index with the trended monthly anomalies of GPP. We're just going to start off with CESM2. And we're looking at slopes here, so grams of carbon per meter squared per year per our change in the Nino 3-4 index. So green would be enhanced GPP during El Nino, brown would be suppressed GPP during El Nino. And we start to see some patterns emerge here. We're seeing a suppression of GPP in the Amazon region associated with El Nino, as well as in South Asia, Oceania, and Australia. Conversely, we see during El Nino an enhancement of GPP in this kind of Alaska, Northwest North America region, the Horn of Africa, a bit of the Middle East. So expanding that out to the rest of my ensemble, we can see, again, pretty similar patterns here. All of the models demonstrate this suppression of GPP in the Amazon basin region associated with El Nino, though there are some differences in kind of the strength of that suppression and also the spatial extent of it. But we also start to see some disagreement in the models, areas where they're not quite reproducing the same teleconnections. So one of them would be that in all of the other models, we are seeing a suppression in GPP in Australia, with the exception of access at the top, where we see kind of a slight enhancement, but maybe not overly statistically significant there. Another region of difference would be this kind of Alaska, Northwest North America region. We see a lot of difference between the models in the spatial extent associated with that. So CMCC there in the middle has kind of an enhancement across all of Alaska and pretty much the entirety of the western United States, compared to IPSL right below that is very small, kind of just along the coast of California. And then finally, one last difference would be that there's a lot of disagreement around what happens in the Congo region. So you can see access up top does see kind of a statistically significant suppression in GPP associated with El Nino, kind of a mixed result for NPI, catty corner there. And then the rest of the models either aren't overly statistically significant or more of a mixed result. So how do we get into then quantifying those spatial plots. One pretty standard way of doing that is looking at the percent of land area being impacted. So I have that here broken out by model, and then there's an ensemble mean along the right side. So just to start off, this is just the land area exhibiting some positive correlation or enhancement of GPP associated with El Nino. Not a huge spread, maybe coming out to about 12% of global land area experiencing this enhancement. Adding in kind of the negative correlations there, it's a bit split whether that is like outweighs the positive in terms of land area or not. And then moving on to finally the total there in yellow, it comes out to about an ensemble mean total land area of 26.5% experiencing some kind of ENSO impact on GPP, which is interesting to know, but maybe not overly informative if what we're trying to get at is the impact on carbon uptake. Because if we think back to our spatial plots, something like Australia is experiencing a lot of statistically significant suppression, which would contribute to the land area being impacted, but that doesn't really have much of an effect on global GPP since that's not an overly productive region. So then I looked at, this is gonna be annually averaged global GPP, the percent of that experiencing some correlation with my Nino 3-4 index. Again, starting off with positive, it's kind of a largish range here. So BCC running very low, like less than 5% of global GPP experiencing an enhancement versus Mirac is quite high, over like 26%. Adding in the negative correlation there, so GPP that's experiencing some suppression, for the most part, that outweighs the enhancement of GPP associated with El Nino by a fair amount there. And then finally, you see our ensemble mean total GPP impact comes out to about 42.8% of our global annually average GPP experiencing some impact from El Nino. So if we think that's a greater amount than our land area average, we can kind of infer from that that ENSO is impacting maybe these smaller, really productive regions of the world. And then a final key point here would be if we look at IPSL, Mirac, and MPI. Those are really kind of standout models where either the enhancement of GPP is more even or even actually outweighs the suppression of GPP, especially with Mirac and MPI. So if we kind of think back to where maybe that is coming from, circling back to these plots, I've kind of grouped them into my group A models, which does include CESM2, which is not pictured here. You see they have pretty large and consistent statistically significant suppressions of GPP in the Amazon basin region, where if you compare that with our group B models along the bottom there, it's really a much smaller spatial extent. And if you kind of think about the Amazon basin region, there's even a little bit of enhancement in GPP, especially in IPSL on the left-hand side. So here's more of kind of an easy way to look at that. I focused on this Amazon basin region because all of the models are showing these statistically significant relationships, and also because it has this, represents a large amount of GPP flux. So here we're looking at just the correlation coefficients broken out by model from our GPP Nino 3-4 regression. I ordered it from greatest to least so it's easy to look at, and then our kind of outlier models of IPSL, Mirac, and MPI are shown in the lighter green on the left. So coming back to our ENSO effects on climate, I'm just going to show the CESM2 results because all of the models show pretty consistent implications with these driver variables. So again, we're looking at linear regressions of the Nino 3-4 index with surface temperature, precipitation, surface downwelling, shortwave radiation, and the general pattern here would be that during El Nino events, we're seeing an enhancement in surface temperature, a decrease in precipitation, and an increase in surface downwelling shortwave radiation associated with El Nino in our kind of Amazon basin area of interest. So expanding this plot back out, I've now included those Nino 3-4 regressions with our different variables, kind of from left to right. You see those regressions with precipitation, temperature, radiation. And you see if we compare our GPP Nino 3-4 regression with our precipitation Nino 3-4 regression, we start to see kind of a similar pattern here. You can kind of say that if there's tight negative correlation of precipitation in Niño 3-4, you would kind of expect to see a tight negative correlation of GPP with the Niño 3-4 regression. Comparing that to something like temperature, which is a bit all over the place. All of the models are showing similar-ish increases in temperature, but it's not as clear of a pattern emerging there. And then similarly, if you look one to the right, the radiation Niño 3-4 box, again, you're seeing all of the models kind of about a 0.2 correlation of radiation to the Niño 3-4 units. So if all of the models are kind of showing similar patterns of the Niño impact on these driver variables, I then looked at how maybe that is impacting, or how the land model is responding. So I tested out all of my linear regressions of GPP with all of the driver variables, and kind of the interesting factor here would be that our group A models are exhibiting a different response than the group B models. So here we're looking at a linear regression of GPP with radiation, and it's CESM2 on the left, which was pretty representative of the group A models. And if you focus in our Amazon basin region, we see this really strong negative correlation between these two factors. So you would expect if there's increase in radiation, kind of a depression in GPP. And then if we look at our group B models on the left, I've shown MIRAC, but this is pretty representative of the other two models as well, of MPI and IPSL. So you're seeing a really strong opposite effect here of radiation, which is probably driving kind of the differing impact of El Nino on GPP in this region. So adding that back into this very scary plot, I've shown again, adding in kind of our GPP variable regressions. Really the important part here would be looking at the regressions of radiation with GPP, and you can see that our kind of outlier group B models of IPSL, MIRAC, and MPI are really out of family with everyone else. So even though all models are experiencing an increase in radiation associated with El Nino, it has this converse effect on GPP in this region amongst these three models. And then just kind of to sum it up, right, group A models. So if El Nino, there's a reduction in cloudiness resulting in an increase in solar radiation reaching the ground surface. You see with the group A models that results in kind of a depression of GPP. Though it's obviously kind of a confluence of factors where if there's less cloudiness, you also see less precipitation, increase in temperature, all kind of driving this depression in GPP. Versus for group B models, you see kind of the converse. They experience similar climate forcings, but a differing response associated with GPP. And then for conclusions, yeah, all of the CMIP6 models showing a very similar spatial pattern of ENSO impact on GPP, resulting in a reduction in carbon uptake during El Nino events. Mainly this is coming from the Amazon basin region, a suppression in GPP there, mainly resulting from precipitation. And then finally, these three outlier models of MIRAC, MPI, and IPSL exhibiting kind of a weaker reduction in GPP in this region due to these models' dependence on radiation. Any questions?
Thank you, Maria. It's a pretty good presentation, and yeah.
Great talk, thank you for that. Did you compare potentially differences in seasonality of changes in temperature, precip, and radiation between your group A and group B models? Like, was it maybe triggering a similar teleconnection but the timing was off, or are they just literally triggering different teleconnections?
Do you mean like lagging the effects, or just generally looking
Yeah,
at
like if the radiation
seasonal
effect or the
patterns?
temperature effect happened earlier in the season when maybe there was more soil moisture kicking around from earlier versus happening a few months later when maybe it was drier. This is a mid-latitude bias, but like similar idea for the tropics. But
I actually haven't done that yet, but that's a great potential like next step. I do think there's possibly kind of that lagged effect of prolonged radiation over time having like a different timing there. Yeah.
So I guess El Ninos are hot, dry, and sunny.
Yeah.
Do you have the statistical basis to do attribution on like which driver is controlling GPP? How like tenuous is that?
Yeah, I am not sure. I think that would be really awesome to do. I think it's hard because they all kind of influence each other. I think it'd be difficult to untangle.
Yeah. And one thing that's worth thinking about is a lot of these models have like large ensembles. And then if you would get more than one simulation per model and more chances at finding situations where they aren't perfectly correlated with each other. Just something to maybe think about.
Yeah, thank you.
That was a really great talk, thank you. I was curious, it's similar to the question I was asked about the seasonality, and have you looked at lagged effects and how, because I imagine radiation is kind of more of an immediate impact on GPP, but something like soil moisture stress could be, depending on whether the model has hydraulics or not, could be an impact a year down the road.
Yeah, I actually haven't yet. I think there was a great paper that was published recently in JGR Biogeosciences that did talk about kind of a lagged effect associated with El Nino because of the prolonged radiation kind of resulting in more heat stress associated with that or water stress. So I think that is a great point. I haven't done that yet, so I think that would be a potential good next step. Yeah.
Thanks, Samir. That was an excellent presentation. It was really nice. I'm curious about kind of the difference between GPP and radiation relationships that you showed between like those three models and the other group.
Yeah.
Is there any kind of like observational basis we can look at to kind of see which one makes more sense?
Yeah, I feel like I would tend to say it's more of group A. I think the observations tend to say that El Nino is like a suppression in GPP, so I think the fact that those three are showing an enhancement seems a little not quite correct.
I just happened to notice that NOR-ESM and CSM showed different amplitude responses with the same land model underneath them. So I guess it just could be interesting. There might be something to learn there by looking at those two models in a little more detail. Maybe it's just an ENSO teleconnection that's stronger, probably, or different looking like ENSO in the two models. But just kind of an interesting possible avenue.
Thank you.
Thank you, Maria, and yeah, we can move to the next speaker,
So this is going to be maybe a kind of weird talk in that it's half or maybe less than half about science and largely about methods and testing out a new method motivated by increasing shrub cover in the Arctic. But mostly because I needed an excuse to do this thing that I wanted to do. And we were supposed to be looking at increasing shrubs in the Arctic. There we go. Okay, so the goals on the left, the goals, the public goals, are that we are going to determine how increasing woody vegetation, in particular shrubs, in the Arctic are influencing Arctic hydroclimate. So the idea here is that as the climate warms, it allows these woody vegetation systems to expand into regions that were formerly tundra. And really what we're interested in is the follow-on effect of that to see how that increase in shrubs is then going to feed back on the coupled climate system. My not-so-secret goals were to determine if we can use something called atmospheric nudging to really isolate the local land-atmosphere coupling effect, so the feedback of shrubs on the local atmosphere and what that does to surface climate in a coupled system without worrying about teleconnections. So the experiment that we imposed here was using CLM5 coupled to CAN6 when they were coupled, otherwise in a land-only situation. And we took everything that was grass, so C3 Arctic, oh dear, I see why you were all.
Takes a little bit, I think you just have to hold down the button and let it sort of.
Everything that was formerly C3 Arctic grass, whatever, all the brown stuff is where the grass used to be.
So you can use the mouse for what it's worth.
Okay, whatever, big brown blob, big green blob. So everything that was normally grasses, that's sort of the default tundra representation in CLM, we took all of it and we turned it all into shrubs. So boreal shrub. So obviously this is not a realistic perturbation, but it's a really big perturbation, which is convenient when you're trying to find a signal. Given the long-running thread of, hey, our shrubs are dead in the Arctic, I figured I should check if these are dead. They're not totally dead, so the shrub LAI is on the left, the grass LAI is on the right, and the difference is the big one on the far right. So there is more LAI when we put the shrubs down, so they're not totally dead, that's good, and increasing shrubs is increasing LAI in the Arctic, which is sort of the experiment we were trying to do, so that's comforting. Okay, so I told you we were using CLM5 and CAM6. We're actually using 3 different sets of paired simulations. So for every pair of simulation, we have the control, which is like the grassy Arctic, and we have the experiment, which is the shrubby Arctic. We have them in a fully coupled simulation, fully coupled if you don't care too much about the ocean. So it's a slab ocean, dynamic atmosphere, land model. And then we have a land-only simulation and a nudged simulation. So I'm going to step through what each of these is. Fully coupled is just the land and the atmosphere are talking to each other. Fluxes from the land get passed to the atmosphere can respond to those and interact. So if you look at the difference between the control, which is the grassy Arctic, and the experiment with the shrubs, you get all of the changes of the atmosphere feeding back on the land surface and all of the changes in the land forcing the atmosphere. The land-only simulation, in order to make sure they have the same base state climate when we're comparing them, we're using atmospheric data that comes from the coupled control simulation, so it has the same default climate, and then we're forcing the land-only model with its grass, and then forcing the land-only model when it has shrubs. But in this case, the shrubs can't feed back on anything that's going on in the atmosphere. And then the last case, which is the thing that I've been wanting to do for a long time and just needed to find an excuse, is this thing called atmospheric nudging. So this is a coupled simulation. We're using CAM, but we're pushing the large-scale circulation towards the control. There's a couple different ways you can do this. You might have seen papers where they sort of set up large-scale circulations to drive heat waves. So you can use nudging within the context of CAM to either force outside of a lat lawn box to look like a certain region, or you can use it the way I'm using it here, which is to force certain vertical levels of the atmosphere to look like the control. So in this case, I'm kind of bullying CAM into looking like a global scale boundary layer model. I'm letting the lower part of the atmosphere do whatever it wants, but once you get above 700 hectopascals, I'm pushing the circulation, so in this case the wind field, I'm pushing that towards the control state so that you can't get any large-scale circulation changes by design. So it's going to suppress any teleconnections. If you're interested in details, I'm nudging this every hour, and like I said, above 700 hectopascals. These were not particularly informed decisions, that just seemed kind of reasonable. You could nudge it every time step, you could nudge it maybe every 3 hours. If you make the time step too big, some shady things can start happening. And if you were looking at different ecosystems, 700 hectopascals might be a bad decision. Okay, so that's kind of the heavy methods section, and I'm gonna leave that behind and go talk about some science for a bit before coming back to it. But I wanna stop and see if people are like, what are you doing? Or if you have any questions specifically about this while the cartoons are there. Yeah.
How strongly was it nudged?
It was nudged full,
Okay,
as strong, yeah, you pick a, yeah, you pick a parameter between 0 and 1, so you can gently nudge it or totally nudge it. I nudged it as strongly as possible, and you can also choose to gently nudge it between a bottom layer and an upper layer, and I was just if you're above 700, go all the way, which is, something a little more smooth would probably be smart, but I just wanted to see what would happen, so I kicked it hard.
What time period is for your nudging? I assume you use observation.
These are not using observations. These are climatological equilibrium control runs. So they're 50-year simulations, fully equilibrated. I guess in some sense, I'm using the modern vegetation distribution. Yeah.
So you nudge to the atmosphere, the original atmosphere.
I nudge,
to the original.
not going to touch the screen, I nudge to this atmosphere. And if it wasn't nudging, it would get to do whatever it wants. But in that case, the bottom gets to do whatever it wants, but the top has to look like that. Yeah.
That was my question.
Same question? Cool. Okay. So, some science happened. So I'm going to show you the difference between land-only surface fluxes over the Arctic on the top and coupled, in particular, the nudged. They look pretty similar for these purposes on the bottom. So, shortwave absorbed, downwelling long wave, upwards emitted long wave, which is a function of surface temperature, and then sensible and latent heat fluxes. So in both cases, when you have more shrubs, because they are tall and stick up above snow and they were leafier into the spring and summer, you're absorbing more shortwave radiation, so there's an albedo effect there. There is no change in downwelling long wave radiation in the land-only simulations by design. You can't have that when you're forcing it with atmospheric data. But in the coupled simulations, you're getting a pretty big increase in downwards long-wave radiation because the atmosphere is warmer. So that is going to drive some warming at the surface. Upwards long-wave radiation, that's a function of surface temperature. You're seeing that the surface is warmer when you have more shrubs. The top one, I have a significance mask on these, and it's basically masking it all out because I'm plotting annual means, but there actually is an increase in temperature in the springtime. And then here's the sort of big difference is that the land-only simulations have really big increases in sensible heat flux, whereas the coupled simulations don't have particularly large increases in sensible heat flux, and that's because the coupled simulations, your atmospheric temperatures can adjust to the warmer surface, so you don't have as large of a surface-to-air temperature gradient, whereas the land-only simulations, you get a big change in surface temperature, the atmospheric temperature has no idea, so you can get these really large temperature gradients that drive really large turbulent heat fluxes. So you see that in the sensible heat flux field of your land-only simulations, and then both coupled and land-only have increases in latent heat flux from the shrubs. Will alluded to increasing shrub happiness, not deadness, this morning as leading to warming due to a bunch of feedbacks. We can use a tool called radiative kernels, atmospheric kernels, to decompose what is driving increases in energy into the surface and attribute it to specific feedbacks in the atmosphere. So I'm going to show you that on this bar graph. If the numbers are below 0, that's like you're putting more energy into the land surface, which you would expect to warm the land surface. And if the numbers are above 0, that means the effect is to take energy out of the land surface. And there's a whole bunch of fluxes here, and I'll step through them almost one by one, but actually more like 2 by 2 or something. So the first thing you see is that when you add shrubs, you get an albedo change. It's darker, so that's leading to more energy absorbed by the surface. There's 3 bars because the solid one is both land and ocean. The light gray is just land, and the dots, the darker gray, is ocean. This is averaged over the Arctic, I think north of 60 degrees. So even though it says global, that just means land plus ocean because I was lazy and I didn't change my script. So more shrubs, darker, absorb more energy. You also get more energy coming into the surface, both because your atmosphere is warmer, that's the D long wave D temperature, so warmer air emits more long wave radiation, both up and down into the surface, and then also that atmosphere has more water vapor, and water vapor is a really good greenhouse gas. So that's also emitting extra energy into the surface. So Abby had a paper back in 2010 that pointed out this water vapor feedback, so it's good that we're sort of seeing a self-consistent thing here. And these are smaller than the albedo effect on their own, but if you add them up, these atmospheric effects are sort of getting to the same magnitude of change as that initial albedo effect. Other stuff happening is that increase in evapotranspiration you would expect to cool the land surface, so more ET means cooling, so that's why that number is going up. And then also there's this upwards direction coming from the shortwave cloud effect. So when you have more ET over your surface, you're getting more clouds, which means you're getting less sun hitting the surface, and that has an overall cooling effect on the Arctic. So it's cloudier, and that would cool, but it's actually overall warming in terms of atmospheric feedbacks because of the temperature and water vapor pieces. Everything else, that big temperature one is literally just like the temperature response, so the surface energy budget has to balance, so you're getting rid of the rest of your energy by heating up your surface. The long wave cloud effects are small, the short wave water vapor effects are small, and the sensible heat flux is not 0, but not as big as sort of the short wave effects or the atmospheric feedbacks. So, more shrubs equals warmer, for a variety of reasons. Part of this is due to the albedo, but there's also a bunch of other stuff going on, some of which cancel out in terms of the atmospheric feedback, but the overall effect is to lead to warming. These are all annual mean. If we look at this instead over the seasonal cycle, this is for our land-only simulation. You see that most of your warming is happening during the springtime, maybe like 2 Kelvin of warming as a result of these shrubs. If we compare that to what's happening in the coupled simulations, the fully coupled simulations, it looks in some sense similar in that the most warming is happening during the spring, but there's also warming happening year-round. The warming is way bigger. It's like twice as big. You're getting warming of around 5 Kelvin in springtime, and the interannual variability is ridiculously large. So if you're trying to find the signal here, it's going to be way harder. So comparing these makes me sad for 2 reasons. Both the atmosphere is changing the magnitude of the answer. Those numbers are not the same. It's about twice as big in the coupled run. But then the variability in the coupled run is just really big in a somewhat demoralizing way. So this is what I was hoping nudging would potentially be useful for. Happy. Like, maybe suspiciously happy. This worked really well, like too well, like, seems like, anyhow, things don't normally work out this well. So it's capturing the magnitude of the fully coupled response, similar timing of response and similar size of response, but the variability is way, way lower because you've suppressed all of that large-scale atmospheric circulation that leads to big interannual variability. So this seems really great, even though I made some pretty arbitrary decisions, like 700 hectopascals. Maybe I should have chosen 800 or 500, I don't know. And I nudged every hour. Again, you can do this as frequently as 30 minutes, which is sort of the official guidance. Maybe you could do it less frequently, like 3 hours. There's some danger there with numerical stimility. I mentioned this blending versus really sharply nudging so you don't get weird looking atmospheric circulations. And then you might want to choose higher or lower levels to start your nudging for different ecoregions. So I chose 700. It wasn't totally arbitrary because the Arctic doesn't have like crazy deep convection or something, but if you were looking over the Amazon and you wanted to capture regional circulations or something, you should probably be choosing something much higher, like 500 or 400 hectopascals to start your nudging. Otherwise, you would expect to literally be suppressing the signal that you're trying to capture. So, pros. We captured the magnitude, yay, and of the coupled simulations, but with the variability of the land-only simulations, which seems great. Also, this infrastructure was already there. I did not have to do any coding to make this work, which was amazing, and it was fairly straightforward to implement. I screwed up a bunch, it took me a couple weeks, but once I figured it out, it was pretty straightforward to implement. So great, let's do this all the time. What could go wrong? A lot of things could go wrong. Okay, so the cons of this, it's really slow to run a model this way. So those of you who look at sort of what the slow pieces of a model are will know that input, output, like reading files and writing files, takes a lot of time. I'm literally getting the atmospheric model every hour to go and grab the full 3D field of another atmospheric model and read it in and push itself towards that. That also means it's very data intensive. You have to store the full 3D field of every hour of an atmospheric model so that you can go and read it. And again, I said these were 50-year runs, so that takes up basically my entire scratch space of the thing I'm trying to push towards. So it's hard to run a simulation when your entire scratch space is already full of the simulation you're trying to push it towards, so it's just not logistically ideal. So it's slower and it's more expensive than running CAM just on its own. Also, I should probably formally check if this is actually technically numerically stable. I was so happy by how good it looked that I didn't go and check if it was satisfying CFL conditions. So basically you're not putting in a perturbation that's too big for the time step. And that could lead to things like spectral ringing that are bad, and you shouldn't do that. So I should check and make sure that's not happening. But if you ignore all of those things, it looked really good. Also, this was expensive, so thank you to the Land Model Working Group meeting for giving me some computer time to run this. Yeah, so where I think this could be useful is global runs where you don't want to worry about teleconnections on purpose. So for instance, if you really want to just isolate what the local hotspots are for land-atmosphere coupling, this could be a good way to do that. Scientifically, it's probably computationally a kind of not great way to do that. It could be useful for regional studies like this Arctic one where you're sort of bullying CAM into acting more like a regional model by suppressing those large-scale responses. Of course, you could just use a regional model and not bully CAM into doing something it wasn't meant to do. But whatever, it's an option. You could do it, especially if you wanted to compare to other CESM runs. And what I'm really excited to do is I think you could actually use this as a diagnostic to identify regions that are likely to trigger teleconnections. So if you run a nudged simulation like I did, and you basically just force it to act like a global boundary layer, and then you look at the total column energy budget, if the local lower atmospheric response was capable of dealing with the change in the land surface, and the energy budget of the full atmospheric column looks fine, great. It's probably not going to trigger a change in circulation. But if that local atmospheric response could not handle the change in the land surface, that's probably an excellent candidate for locations that would be likely to trigger a large-scale teleconnection. So somewhere you might want to investigate down the road. So to wrap up, nudging seemed to actually work pretty well. It captured the magnitude of coupled responses with the variability of a land-only simulation, and the sort of science result is that more shrubs equals warmer because of atmospheric feedbacks. If nobody has ever watched Monty Python here, these little GIFs they're from a movie where this weird little creature in the forest demands a shrubbery, and because we're talking about shrubs, we imposed a shrubbery. So, yeah,
questions.
Any question?
One right in front.
So, just to be clarifying, the nudging is like you run the global model, but you nudging for the Arctic region.
You can run it that way. That is not the way I ran it. I let the entire lower atmosphere do whatever it wanted, and I nudged everywhere globally above 700 hectopascals towards the U and V winds. But I only imposed a perturbation in the Arctic, so nothing really interesting happened outside of the Arctic because there was no surface perturbation. But you can run it where you let the full column do whatever it wants, and then on the left and right and north and south, you push towards other the control.
So the nudging only applies to the UV winds.
I only applied it to UV winds. You can also apply it to temperature. You can technically apply it to moisture flux, but it is physically inconsistent if you do it anywhere above the bottom layer. But in the code, you could nudge whatever you wanted, but there's reasons you shouldn't do that. I only nudged the wind.
So you're saying it's more expensive, but that's per simulation year.
Yeah.
You might expect to need many fewer simulation years.
Right. Yeah, because there's way less variability.
Yeah.
And also, if I was going to run every single point in a coupled simulation, I could just do this instead and only run one simulation instead of 500. Yeah.
I think another cool application is to use the regionally refined version if you were interested in a high resolution. And you could do the same. Essentially, it's allowing CSM to be a regional model, really, is what this does, which is kind of interesting.
Really want that isn't built in, I would have to modify the way the nudging is implemented, is I want to be able to prescribe a 3D box where I nudge or don't nudge. Right now, you can either do the full column and nudge outside of Latin lawns, or you can do everywhere Lat lawn and nudge vertically. But I'm sure that's doable.
Just a point for everyone, if you're running out of scratch space, you can ask for more.
Oh, really? Not give me that.
I mean, they can say no, but they usually say yes, so I think, don't be afraid to ask for more, right? That's not a good reason not to do something. Unless you ask for
You can get 100 terabytes.
Oh,
yeah.
Okay. Someone's gonna be hearing from me.
So, I mean, speaking of that, scratch space issue and the need to kind of read in, the atmospheric variables every hour to kind of nudge the model is, I don't know how CAM works with nudging, but for instance, in WRF, I think that there's and maybe it's the vertical nudging that's different, that sort of nudges towards a temporal tendency rather than an external data set. I don't know, what your thoughts on that approach and how that might be. And I think what that is designed to do is just sort of not let the system run away too quickly.
Yeah. I really don't know. I think there's a ton of digging into exactly how the nudging is implemented and what fields it would make sense to nudge and what fields it wouldn't make sense to nudge. And nudging pressure might be kind of fun. It's not really built in there, but for my purposes, it might be kind of fun. I think there's lots of space. I was just using the low hanging. What's the easiest way I can make it go?
Hey, that was really great talk. I'm just curious, is there a way to calculate the difference between, the fully coupled law with the nudged law? Because for each year you have, for example, let's say you have variables like geopotential. You can also calculate difference in temperature. So that would give you, quantitatives to be compared to your local feedback.
Yeah.
Because right now, especially for some extreme event attribution, right, we are curious about how local feedback is, how annual variability could influence that. So if you do the difference between, each year between the fully coupled and also the nudged one, and compare with your, local feedback, that could do, just to have some.
Yeah.
Maybe comparable, I don't know.
That's a great suggestion, especially because I did push it, I used the full 50-year control simulation to nudge towards. It's not like I just repeated the same year over and over. So those differences should be in there.
Yeah, especially if you have, for example, for Arctic areas, some heat wave, corresponds to a certain atmospheric pattern, right? If we try to find some similar patterns, compare some extreme cases. I don't know if that can have some implications.
Yeah.
Yeah, it's a great idea.
Okay, thank you, Marissa. And next speaker is Anna.
Okay, thanks. Okay, yeah, thanks. So this has been really great. I've enjoyed all the talks today, and kind of been a long day, but we're almost at the end. So I'm actually going to switch gears a little bit and talk about some developments that have been going on with the Joules land surface model, which is really similar in a lot of ways to CLM, because I've been working the last 11 years until last August in England. And so I'm kind of going to summarize about 8 years of work. And there's been a lot of other people who have contributed to this. So Arthur, Emma, Sikai, and Evan were all postdocs who have worked with me on some of this. Peter Cox, along with Arthur, and another one of Peter's PhD students, John Moore, developed the demography model that I'll talk about. Andy and Eddie are both at the Met Office, and they're like the ones who make sure that any developments in Joules get into the official configuration that goes into the Earth system model. Danny and Dayu are stats people who have been helping me with emulators, and I'll talk a bit about the applications of that. And then, Caroline is a technician who's been really instrumental. And then we've got some people from forest research who have been giving us lots of data. So I just want to give all those people their credit. So what I'm going to talk about is I'm interested in land-based mitigation and trying to improve the representation of it in Earth system models. So I'll talk a bit about the case for including that. I've got a wish list of processes that I think should be included in all Earth system models ideally, but I'll talk specifically then for the rest of the talk about what we've done in Joules to include bioenergy crops and managed forests. Then I'll have some concluding thoughts at the end. Okay, so why might we want to represent land-based mitigation and managed land? Well, land use change and managed land already play a large role in the global carbon cycle. So from the last global carbon budget, about 12% of human emissions of CO2 each year come from land use change. So that's a huge impact of land use change. Also, though, even if we think about the natural land sink, so about a third of the carbon that's emitted each year is taken up by the land surface. And we tend to kind of think of that as like a natural process, but actually about 2/3 of the land surface is managed. So we really need to include human management impacts on the terrestrial biosphere if we want to be able to represent even just historical changes in carbon. The other thing, so that's thinking about the past, looking into the future, land-based mitigation plays a major role in most scenarios, not even the scenarios that try to highly mitigate climate change. So most scenarios include some degree of land-based mitigation. And that's either bioenergy crops that are coupled with carbon capture and storage, or through afforestation and reforestation. So this was a paper by Stephanie Rowe a few years ago that showed that a quarter of emission cuts by 2050, and these scenarios for 1.5 degrees come from the land sector. So we need to be able to represent these things. But they could have a really huge impact potentially on the land and on land atmosphere feedbacks. So in the CMIP5 scenarios, the median land requirement for, so looking at all the scenarios that meet a 2 degrees target by 2100, and looking at how much land in those scenarios went towards bioenergy crops, the median amount of land that went to bioenergy crops in those scenarios was equivalent to about 2 times the size of India. So it's a huge amount of land converted to whatever it was before to bioenergy crops. And even if we think about afforestation and reforestation, which fall under more natural climate solutions, that's also equivalent to about 1 time the size of India. So again, a really large conversion of land to forests. And so what I'm really interested in is kind of 2 questions. How would these land use changes impact ecosystems and the climate? And then also, how would they actually be effective at removing the CO2? So in these scenarios, these scenarios are generated by integrated assessment models that assume that these land use changes
are effective climate mitigation strategies, but the IAMs don't include climate impacts and feedbacks. So actually, are these actually effective methods? And also another motivating thing is thinking about national, so that's on a global scale, but on a national scale, countries are now really considering how can they meet net zero targets and what role can the land surface play in that. So for example, in the UK, they have legislation to meet net zero emissions by 2050. And this study a few years ago from the Royal Society, they saw like how much could we cut emissions by 2050, being really aggressive. And they came up with 130 million tons of CO2 emitted each year, even with really aggressive emissions reductions, just because some sectors are more difficult to mitigate than others. So that means that that's the amount of CO2 that needs to be removed from the atmosphere each year to meet net zero. And so one question is, how much could woodlands play a role in this? So that's a motivating factor for one project that I'm on that I'll talk a bit about. And so, so we need to think about how Earth's models can maybe help us answer some of these questions. And the model that, as I mentioned, that I use is called Joules. I won't go through all this because if you're familiar with CLM, so it's really similar stuff. It does a lot of the same things. But here's my wish list. So these are things that I think we need to be able to represent in models. So when we're thinking about planting bioenergy crops or growing forests, we should be able to represent the carbon that's stored in those as that's the most important thing. And Joules and most models, yes, we do that. That's what they're made to do. Similarly, we're able to represent surface energy fluxes, like the talk that this showed. There's impacts on latent heat flux, sensible heat flux. But one thing that maybe we don't represent so well is seasonality of that. So like if crops have a different growing season, then they'll have different latent heat flux impacts than crops with a shorter growing season. So even though there's a check there, it's not, I wouldn't say it's completely done. The next set of things have to do with the management practices. So the yields of bioenergy crops, forest growth cycles. So by that I mean forests, there's not a tree that just magically appears and it's a forest. So we have different size trees depending on when they're planted. So being able to represent the fact that trees start small and grow large, we need to represent that. We need to be able to represent management options like thinning, harvesting. So in Joules, this is what I'll be mostly talking about for the rest of the talk, is some things that we've been doing in that space. And another thing that's not quite there yet is we want to be able to maybe represent tree species that are of interest. Talking about, say, for example, the UK wanting to plant trees. They want to know more than should I plant a needle leaf evergreen tree? That's not useful to them. They want to know maybe something more specific than that. The rest of the things on those bullet points on the left are things that we're not quite there yet. So growing seasons of crops, as I mentioned, they might have a longer growing season or a shorter growing season. A major crop that's assumed to be used in these scenarios is miscanthus, which is grown during the year and then during the summer, and then it's left over winter to dry out. So during the summer it's green, and then over winter it's dries out, and it's we'll have a picture of it in a minute. It's light colored, so it'd have a different albedo impact than if you had harvested the crop and then had soil underneath. So we need to represent that. We need to represent these kind of albedo impacts of different land cover types. Impacts of irrigation and fertilizer inputs. So these impact not just the nutrient cycles, but also wouldn't it be great if we had nutrients that run off into river and can affect biodiversity in streams and that sort of thing. And biodiversity also just in forests and the landscapes themselves. So some studies show that planting some kinds of bioenergy crops might actually increase biodiversity. Others show that they don't at all. There's a lot of studies that say having monocultures of anything is bad, and we need mixes of species. But we can't really represent this in our Earth system models now, but these are the kind of questions that I think we should be able to answer. Okay. Oh, so I'm really interested in kind of summarizing where all the Earth system models are right now on this. And through this project that I'm a part of, ESM 2025, it's an EU-funded project. We've got some work going on to do some benchmarking of the models that are a part of that, but I would love to include more models. So we do have CLM fates included in that, because Rosie Fisher is on the project. But yeah, if you're interested in this as well or have information, then please send me an email. I'd love to talk to you about it. Or just talk to me. I'm here. Okay, so again, I'm gonna talk quickly about what we've done in joules. So yeah, here's bioenergy crops in southern England in February. So this is what they look like this time of year. They would have been harvested, maybe a month after this. So there's the picture I was trying to explain earlier. All right, so Emma Littleton did some work a few years ago to include a representation of miscanthus in joules. She calibrated it against some flux sites in England and got a pretty good fit. That's what the plot on the left is showing, so that's GPP. Then she compared it against a data set of yields, and there's a pretty good fit over Europe, but it tends to overestimate the yields in the southern US, so in hot places, this miscanthus tends to be overproductive. Then another thing that Emma did that was really interesting was she compared predictions from joules to two other kinds of predictions of miscanthus yields of different kinds of models. So the top one is Miscanfor. So this is a dedicated miscanthus crop model. And the 4 stands for Fortran, not forestry, which took me a few years to realize that. So that one's developed out of, we have colleagues at University of Aberdeen who work on that one. And then image, when it makes its prediction, that's an integrated assessment model. When it does its scenario predictions, it does have models that represent yields from crops. So yeah, that's what's on the bottom one is the results from image. And on the left is the yield, and then on the right is the soil carbon changes. And the main thing to point out is that you get really different answers depending on which kind of model you're using. So Miscanfor assumes that all the there's a high temperature threshold and the crops just die. So that's where there's some gray up there. Joules, as I said, tends to be really productive in the hot regions, and that's quite different from what image shows. And then the soil carbon changes are also drastically different between the different kinds of models. So yeah, we have really different assumptions about yields, about heat tolerance and soil carbon impacts of miscanthus, and also just kind of don't really know which one of these is really correct. Because, for example, these are showing results in the tropics, and I don't know of any experiments of actually growing this crop in the tropics so that we could actually say which one of these is correct. So that's a problem. And an example of how this kind of affects what we say about how effective land-based mitigation. This was a study that I did a few years ago where we compared 2 different land use patterns from the image integrated assessment model where they planted bioenergy crops. Anywhere where it's red are places where the yields from that bioenergy crop didn't make up for the losses in soil carbon that occurred due to the land use change. So there are large areas in the scenario for 1.5 degrees where you never made up that initial loss of soil carbon. And this was before we had the parameterization for miscanthus, but I had 5 other DGVMs run the same set of experiments and had generally the same general conclusion. So I'm fairly confident that yeah, there are some places where we should just leave forests intact. But also we need to better be able to model this stuff. Okay, so then speaking of forests, on to forests. So on the forest side of things, Arthur Argolds has, along with John Moore and Peter Cox, they've been working on this demography model called the reduced ecosystem demography model. Robust, I don't know, I forget what the R stands for now, sorry. So anyways, so FATES, from my understanding of FATES, it's a 2D cohort model, so it represents a cohort in terms of size and age since disturbance, and red is slightly simplification of that, so it only represents the size, so mass classes over time. So that's what these nice animations are showing, is number density on the y-axis against the tree size on the x-axis. And so Arthur and John have calibrated the model quite a lot against data in Brazil and in the US, and it works pretty well. So now we've been applying it to this project in the UK to try to help kind of inform land use decisions there. And so this is a paper that Arthur wrote last year, comparing Jules red at an even-aged conifer stand in northern England. And on the top axis, so the lines are from the model, and then the circles are from this thing called the Woodland Carbon Code that the UK equivalent of the Forest Service produces, that tells you how much carbon you can expect to have in trees of different ages and species. So this is for Sitka spruce, so a kind of evergreen tree. And you can see a couple of things. So the line that matches the best with the solid colored circle observations there from Jules is the one where we have it's where we have no thinning and no CO2 effects, which makes sense because these forestry inventory models are kind of empirical models that don't assume CO2 fertilization. The X on there is the actual observed biomass at this site, and it is a site where there is thinning. And the best fit that we get to that one is when we include the thinning and also include the CO2 fertilization. So this was interesting because it's a conversation that we've been having with the foresters who are like, I don't know, it's really interesting to talk to them about CO2 fertilization because they don't think it's that important. And then, from our modeling community, we think it's like the most important thing. And I would guess the answer is somewhere in between. So this has been an interesting experience. And then the last thing we're trying to do is to calibrate some of the parameters in Jules to be able to represent some of these different kinds of species. And we've got this, hopefully soon to be automated system where we can run an emulator of the model, calibrate some parameters, and come out with some new sets of parameters that will give us different species. So that's being worked on right now. Okay, so summary, we've been working on all these things. In Jules, there's lots of things that we should represent in Earth system models that we don't right now. And another thing that I hopefully convinced you a bit about is that there's huge uncertainty across the different models. This one project, ESM 2025, we have some common idealized experiments using these 4 models at the bottom there, where we're trying to just look at, if in idealized land use change scenarios, what are the different impacts of these different kinds of land-based mitigation methods. So that's something else being worked on right now. And then I'll just end with kind of a couple philosophical thoughts on this. So I feel like we're moving into a new era with Earth system models where the needs of the end users are becoming more important. So for example, the work with the representing species, we would have never thought 5 years ago to try to represent a specific kind of species in Jules, but that was something that came about from working with the stakeholders. So that's kind of interesting, this idea of hearing from people who use the models what things they think are needed in them and kind of going from there. And then also, if we're trying to make these models more usable by society, we need them to be actually usable and not require a count on derecho. And also, because there's so much uncertainty, it just doesn't make sense to give one answer because we know that we don't know the answer. And so I think really including uncertainty quantification, which we can do with emulators or other methods, I think that's something that we really need to be considering also. And that's it. Thanks.
Question time.
Thank you very much. I'm curious about whether you're aware, or if you do it in Jules, or whether you're aware in the ESM world that actually land use decisions actually these themselves are in the ambition to be modeled.
You mean like actual decisions, like in the
Yeah,
model?
where to change land use and cover.
Yeah, I mean, I like, because the scenario, it's still something that's like external to the model, right? Like we still use scenarios of the land use change. Yeah, so that's not something we're thinking about including currently. It would be really interesting though, yeah.
That was really great, thank you. I have a question, how do we add more species? I'm thinking about the number of parameters that we add and still make them faster.
To add the species?
Yeah, and still maintain, like, if your goal is to have the models run really fast, but if we add more species and more parameters, I just think that increases the computational time, doesn't it?
Yeah, so what I'm talking about here with the fast models is I don't even mean running like the actual CLM or Joules. I mean like running an emulator of it or some kind of machine learning, application where you're not running the full model, but you're running a model of the model in some kind of like accessible interface for end users.
Yeah.
Okay,
We have 2 more questions.
I'm curious about the soil carbon losses you showed with the bioenergy. Did that depend on if you're converting from grassland or forest? And then how deep were you like integrating across the soil profile?
Yeah, that's a great question. And so, so in Joules, kind of anytime if you replace a productive plant with something that even takes a few years to kind of spin up and become productive, then you just have huge soil carbon losses because you've lost that input, the litter inputs. And so that's what happens in Joules. And then, but interestingly, I showed the Miscanthus. They only assume soil carbon inputs from Miscanthus because that's what a lot of studies actually show is that because they, they develop rooting systems, and so that's their assumption, and so their results only show increases in soil carbon. I think there needs to be some. Again, it's like needs to be a bit of both. I think consider.
There you go. So.
Yeah, it's really more just a comment. I mean, it's great to see this. I'm really glad you here shared all that. And like we could have given, as you know, essentially the same presentation for CLM, right, with almost the same goals and a lot of the same successes and not successes. Slightly different, right? But just whatever, some set of. And I would add to this point here, I think the one that we're thinking about the same kind of thing is making ESMs be more relevant. And that's one of the reasons why we've been pushing down this road of the PPE and calibration is to be able to move to a new system and be able to calibrate the model quickly. And so you're also talking about adding the ability to create a new plant functional type to bring it to the new system, which I think is like a variant of the same thing. So I think, again, it's just like an interesting overlap of thinking, so.
Yeah, sure.
So.
Thank you.
Cool. All right,
Peter is the last speaker today.
Cool. Well, the best part about coming last is we've had a really great day of like people introducing the whole idea of having a system framework and having emission-driven simulations and the importance of doing that. There's been some really great talks on that, like just following up Anna, it's really great because we are going to be looking at some of that land use stuff and the human activities in the Earth system model. But where I'll start with is this is a project that we have NSS funding for, which is looking at, it's a growing convergence research project which goes across NCAR, so there's myself here, Dave, Simone Tilnes, Andrea Smith, and Monica Morrison here, between here, an ACOM and Comet program. And then we have Arizona State University, we have Michael Barton, Louisiana State we have Cheryl Harrison, and then at Duke University we have Tyler Pelganau. So this is what sort of covers a lot of what we're doing here is the underlying part of climate interventions with carbon dioxide removal and also looking at solar radiation modification. So I'm not going to belabor the point, we've seen a lot of this, but basically the drive within the policy sort of framework is looking at more emission-based simulations and evaluations because that's the space where you can get
contribution targets. That's where countries can bring their NDCs, their nationally declared contributions, and bring that into space. And as we can see, that to get to some of the Paris targets of 2 degrees or 1.5 degrees of warming, big cuts from like where the actual current policies are. So we're probably not going to make 1.5 degrees unless we start looking at doing some deliberate actions within the climate system. We're probably going to have overshoot, and which means that we're going to have some form of carbon dioxide removal to address overshooting like some of these targets. And the project that we're looking through is like sort of saying, well, in response to this climate challenge, what can we do with our Earth system models? And if you look at how do you get to these sort of like really low 1.5 degree worlds, they require a lot of components to them, and a lot of them are land-based. So they're bioenergy with carbon capture and storage, or looking at reforestation and afforestation. And there's always going to be some level of like hard to mitigate emissions that have to be addressed. So CDR and negative emissions are going to be part of that space. So this is coming to the Growing Convergence Research project that we were awarded a year ago. And this is looking at generating actionable research to investigate combined climate intervention strategies for stakeholder use. As I said, this goes across these institutions. But we're looking at going way beyond just the research community. And this is what Growing Convergence Research is all about, is taking all these different researchers and then bringing them together with stakeholders. In our case, we're working with community partners such as the World Wildlife Fund, the Nature Conservancy, looking at how do we tie back in with government relations, and then looking at other government organizations and industry groups as well. So what sort of things do we talk about when we talk about climate interventions? Well, there's a whole range of things, and we have a couple of National Academy reports that sort of cover some of these things. But this diagram sort of is nice and starts saying, well, to reduce global warming, the first thing you've got to do is basically mitigation. There's no way around that. There's no idea that you can just do some form of carbon dioxide removal to offset the mitigation requirements. But the thing is, there are hard to abate emissions, and also society and economies are slow moving. So on top of that, we're looking at some solar radiation modification here through stratospheric aerosol injections and marine cloud brightening. And then beyond that, what we would like to do is say, well, can we understand how impacts and suffering work in these particular worlds, these mitigation worlds, and these then climate intervention worlds. Okay, so this brings us to what we're doing here in the project. And so we're using CSM, and we're building a new ensemble of simulations, which is what we're calling the Community Climate Intervention Strategies Ensemble. And they're basically starting off along the mitigation pathways. And we wanted to do that in an emission space. So obviously this is CMIP 7 coming through, and this is sort of like what was proposed at Reading last year. And we already have fossil fuel emissions for SSP 119, 245, and 370. So we're going to use an emission-driven version of CSM, configuration of CSM, to be able to use these as our baselines, our starting points. And one of the things we want to do with that is basically put a current day land use continually through these baselines out into the future, so that we can do the CDR, land-based CDR, off of those in a clean sort of manner. The other thing is when you work in a group, you have a lot of competing ideas about what's really good. And so we have this idea that we needed to have active fire aerosol emissions in there. We need to have the biogenic volatile organics in there as well. For the ocean biogeochemistry, we wanted to have the coccolithophores and this new ocean biogeochemistry that allows you to drive a fisheries model. And then we want to do ensembles of these experiments as well. And so this adds complexity, but it also means that we get a much more nuanced and responsive impact model out of them. What I'm going to say is we're going to do these climate interventions off these, the medium and the high SSP, so we can see how they impact in an emission space. And finally, we don't want to do a large amount of model development. So what we're trying to do is work out ways we can do interventions using existing parameterizations and forcing files. Okay, so basically the task to get these baselines working, and this is what we've done so far, is we've got ourselves a large computing allocation, and we've built up an ensemble, the CCIS ensemble GitHub repositories for each CSM component. And so we're keeping track of that, and we're developing the model of CSM 215, which is the CSM 2.1 model that runs on derecho. The new Marble model comes in, and so we have this new ocean ecosystem. It has 4 phytoplankton groups and then 2 zooplankton, and then the coccolithophores. Fortunately, we have a lot of expertise here at NCAR. So Kristen Crumhart and Keith Lindsay, thank you very much for all your help in getting this running. These things are non-trivial, and you think like, okay, we'll just do it, but it doesn't quite work the way you expect. I'll show you in a little bit that it takes a little while to get the model back into, spun up and get it into balance with the CSM 215 climate. We're also updating the CLM land cover data sets, so they're going to allow us to do a lot of the reforestation, afforestation, and this is work we've previously been doing, but this will be in the CSM 2 PFT and CFT data sets. We also need to be able to put in bioenergy with carbon capture and storage, so BECCS. So a lot of things that Anna brought up, these are the things we're bringing into the model. And finally, we had some known bugs, such as the fund fixation bug and low irrigation targets that we wanted to address. Finally, we wanted to work out how to use the fire emissions and Megan to have this extra feedback. And so this is like working how to use CAM6 with fire and Megan to basically do aerosols without doing the full CAM chemistry, which is really expensive. So this basically replaces the values that come into the CMIP6 emission files when you would be just normally running the model with values that are directly being specified by those 2 models. Okay, so this brings us to like a point where what does the model look like? And so this is an 1850 spin-up that we're doing. So starting off, and the purple lines are with 1850 CO2 concentrations. The red line is the flat 10 system model, just for a comparison. One of the things we worked out is we need to get this model into full balance in 1850 before we put it into a system model, because it's basically out of balance. And you can see the top left panel shows you what happens with the land surface flux of CO2. And you can see that basically there's this initial drawdown of carbon, and then we're coming back into balance over the time period. We found that the ocean model was actually, even though it was spun up for work that Kristen was doing, was actually quite a long way out of balance for the version of the model we had. And it started off drawing down 5 petagrams of carbon at the very beginning and sort of like converges out to 130 petagrams of carbon. At 130 years, it's closing on 0. So you can add those together and you can sort of say, well, how's the model converging? And we can see that through this net CO2 flux. And we basically want to hit this line of 0 petagrams of carbon per year to be consistent with what the CSM Earth system model would look like, which we did in the flat 10 simulations. The other thing is that when you're running the model, you have, even if you're in a CO2 prescribed mode, it still keeps track of the CO2 tracer. So this final panel shows you how the carbon's been taken out of the atmosphere to bring the ocean and the land into balance. And so when this line here at the bottom, the purple line goes flat, we'll be in balance. Interestingly enough, the CO2 concentration out of the box of the Earth system model is about 287 parts per million in 1850, and 284.7 is what we would hope to hit. So if we have a little bit of drift, we could maybe, like, when we put it into Earth system model, we'll probably end up being about the right CO2, but we've got to run the model out as far as we can. So basically what's left to do? Well, we have to finish off this simulation, get it into balance, and then we have to transition into an 1850 Earth system model configuration with that CO2 that you saw there, the 287 ppm CO2. So you start off with a new atmospheric initial conditions file, so you can actually start that up, and then the CO2 will be evolving as it's running along through the 1850 component of this. We also need to get the version with the active aerosols because it currently has a strong cooling effect when you bring the aerosols online. We're trying to diagnose why that's happening. Once we have the 1850 spun up for the Earth system model version of it, then we're going to transition to historical runs. The idea is to run 4 emission-driven historical runs plus a 5th concentration-driven run as a carbon and climate reference. So we can actually see how our ensemble of emission-driven runs look compared to a concentration-driven run. And then we're running the baselines out. So we have to run these baselines out from 2016 to 2100 for these different SSPs. And they will branch off the end of the historical runs. And finally, we're developing these 8 climate intervention pathways that go off the baselines. So there's a lot of simulations to be done, but we have like a 5-year project. And so we're doing it step by step and getting like the most relevant ones done first. Okay, just going back. So what are we looking at? We're looking at 2 different atmospheric SRMs. For stratospheric aerosol injections, we're very fortunate that we have simulations already done, which give us stratospheric forcings for what SAI would look like. We're also working with the ARISE group on what marine cloud brightening will look like. We're looking at doing reforestation and afforestation scenarios, which is work I've already done with Stephanie Rowe and Maria Val Martin's group. So Stephanie from World Wildlife Fund now, we are developing those scenarios. And again, those scenarios are being built along guidelines from our partners. We're looking at bioenergy with carbon capture and storage. Dave brought that up earlier, and I'll just do a quick slide after this. And then some direct air capture, which is like, what are the feasible limits in terms of like technological spin up of direct air capture? Finally, looking at ocean CDR. And we might not get all to these in the next year or two, but we're like going to be building on top of this as like a longer term project. So we can see in the same framework, this emission-driven space, how the whole climate system responds to these deliberate actions within the system. Again, that will be on the 2.5 and the 3.7, the 70, sorry, the 245 and 370 baselines. And again, we don't want to be doing large amounts of model development for this. So what I'll just quickly show you is, this is work that Stephanie did it through her PhD, and we developed these scenarios of reforestation, which are derived around making sure that we don't take away from agricultural land. We ensure protected areas, so the World Database of Protected Areas, we don't do reforestation or afforestation there. We also ensure that these are in areas that are climatically suitable for reforestation. This is work that Yang Chen, and both of these 2 studies have just recently been published as well, but this is looking at the bioenergy crops in CSM. So we have miscanthus and switchgrass. So this is all code that works and is in CSM right now, so bringing that in onto the experimental framework, it's a matter of just transferring it across. And finally, just talking about the stratospheric aerosol injection components, we have these ARISE simulations where you're going to use for guidance on how to do those. I'm going to leave this to the last slide. This is all being done as part of a community that was sort of built up over COVID. It's called the Community Climate Intervention Strategies Program. We have a steering committee for it. It goes across universities, and we have included within that DOE contributions. We've had people from basically all over the world giving talks through. We had a series of workshops, a series of webinars, and then we also have AGU meetings. And that's where we are right now. It's a project that's still spinning up, but we're really excited to be involved in that. And I think this is an area we can learn a lot about our model in an emission-driven space. So I'll leave it there.
Thank you, Peter. Any question?
Are you running with interactive fires or producing CO2 that are going to the atmosphere?
Well, not just CO2, it's also aerosols.
All everything else.
Yeah,
Wow.
exactly. So, and so it's a matter of how you have these emission factors that convert the black carbon and all of the different sort of species that are coming out of the fire model into aerosols. And it's not as straightforward as I thought it might be in terms of the rate of response, but yeah.
Cool. That's awesome.
Yeah, Peter, really interesting talk. Do you imagine, I mean, maybe it's not part of the currently envisioned simulations, but right, I think the intersections of some of these interventions and some that may sort of like solar radiation management might actually interfere with bioenergy production. Yeah. Like, have you thought about like
that's explicitly the next stage after we get this framework up and running, is to do like combinations of different intervention strategies, especially driven by stakeholders. Yeah. So there are certain stakeholders who are going to be very excited about reforestation, afforestation, or marine CDR, and not so excited about like marine cloud brightening or stratospheric aerosol injection. So we want to be able to do those combinations and see how they all work in the same system framework.
Peter, a lot of good stuff to discuss, but just a follow-up questions about the stakeholder, because like, the model you use, like, is what kind of like resolution, probably depend, stakeholder are interested in, some of them might be very interested in some very high resolution. Right?
Absolutely.
I mean, can you elaborate, some like, the efforts of engaging these stakeholders, or what kind of
Right.
types of stakeholder you're talking about? Yeah.
So, and you're exactly right. Like, so we have, like, two of our key stakeholders are really interested in global perspectives, like WWF and the Nature Conservancy are both very big into forest potentials from both conservation background. But then we also have people who are interested in water management. And we have to be honest about the limitation of our models and the limitations of what we can provide for them. So we can hear what they want, but if we can't deliver it, we have to be honest and open about it. Yeah, we have a stakeholder meeting in April down in Arizona, and we do have very wide range of stakeholders coming to that. We're trying to listen, and the convergence part of this is really very exciting because it's like, what can researchers do and how do we listen and how do we hear what people's needs are rather than assume what they are, assume we know what people would require from us, and then being honest about what we can and can't do.
Yeah, sorry. So I'm curious whether in this project there is like mechanisms set up to like, because I know like we are in the stage of running the simulations.
Mm-hmm.
Like how does mechanism to support translating this model results into like actions, because this is about like
Right.
actionable.
And I think that's the big point is, and we realize that it's a mistake for us to think we go and talk to the land managers. What we need to do is we find people who work with the land managers, people who have boundaries sort of spans, people who understand the models and also understand the management that's required. We don't feel like we have the expertise and knowledge to be prescriptive of like, this will be beneficial for you doing something in a certain part of the world. Yeah, and so it's always about finding people who work with other people, not us working with the end users of the data.
But like, as you mentioned, you have like this stakeholder engagement, so you do take into their consideration into like in the modeling process.
Yeah.
So how's that look like?
So it's interesting. I mean, we are organising this workshop down, but we did a scenarios workshop like a year and a half ago as well, like here in Boulder, and it's just trying to engage like people who are vulnerable communities, engage people who have influence. So like with World Wildlife Fund, they have an international network and they have people in country and they have managers like right down at a very local level. We would never talk to those people. We will talk to the people who are their international sort of coordinators. And so, and we're listening to, well, what do people need? And we're basically trying to take what the research community is doing right now and put it in a sort of like a consistent framework, being able to like put all of the output from that model and be able to then process it in a way that is responsive to their needs. But we don't know what their needs are to start with. So we're basically dumping everything on the model. We've got like, monthly, daily, 6-hour, hourly data coming out. So it's a big amount of data. It's coming out of CAM, CLM, POP. It's like out of every component of the model. So that is a big part of what we're doing. But
Go ahead. And while you ask this question, I have to remind that we have about 8 minutes left, and this is a general discussion, so you can also ask questions to our previous speakers. So yeah, go ahead.
Thank you. I have a question about the SP1 1.9 pathway. Basically, IAM say there is plenty of CDR already in that pathway.
Yeah.
So is your build or your implementation in CESM of that pathway, does it differ from the CMIP6 style?
Absolutely. So that for all our baselines, we have current land use running out to 2100 from 25.
Right, yeah.
2025. So basically, to be a little bit more technical, so what we do is we run a 2015 on the historical. From 2015 to 2024, we're running SSP 245 with everything. And then from 2024 to 2100, the land use goes to just whatever is in 2024. And we take the spatial pattern of 245, but we keep the amount of wood harvest constant. So what we want to do is basically, we want to have a baseline that we can do things off. Because one of the big questions is when you use the SSP framework, how do you deal with the fact that like there's all this spatial sort of heterogeneity, different parts of the world are changing, and then you try and do land use on top of that, you try and do reforestation, and well, no, they actually put some biofuels in here or whatever else. What we want to do is have a clean sheet to do each of these interventions against. And that clean sheet starts in 2024, well, 2025 really, and then, yeah. Does that make sense? And we're building it, and you asked the question of Anna before, like how do you build scenarios? And we have a group working on the scenarios. I have, that's what Tyler Felgenhauer, who's at Duke, is like coordinating. But we bring the literature together, we have tools that we've already used for other studies, and saying, well, what's a reasonable amount? And typically it's like, it's this 10 million or like, 9 million square kilometers or 900 million hectares is the sort of like the top target. But we really want to focus that as well in areas that are going to give big returns in terms of carbon. So there's a lot of areas you can put trees, but you get very little carbon back for.
Questionable, any presenter, like, it's not too much time, 6 minutes, open discussion. Yeah, that's good. Josh, can you unmute yourself?
Yeah, so this is for Peter. I'm wondering whether sounds like your group is working on putting a lot of energy into these scenarios. One of the things that was a little bit of a disappointment about LUH2 was that they never quite got the bioenergy prop field filled. Yeah. So we don't, those of us who don't feel qualified to sort of make up a scenario couldn't use that. I'm wondering whether you're going to share the scenarios like the for people to use with other models, with like regional models or other things like that, so they could do some sort of parallel comparison work or anything like that.
Yeah, thanks, Joshua. Yeah, no, this is a community project, and so like all the scenarios will be provided to the community. We're also engaging with Maria Valmartin and James King and James Weber to do some of these runs with the HAD-GEM model. But we would be very interested in other modeling groups as well. We don't really want to start up a new CMIP because there's enough of those out there, but this is like a small group of models we would like to start with. And if we can get a protocol together and we find something valuable, then it could be expanded. But right now, we don't want to be a single model simulation, single model project, but we don't really want to have the whole sort of spin up to a whole CMIP type MIP either. So, but the scenarios will definitely be available. All of the output will be available as well. This is a community effort.
Thank you for that clarification.
And we're really fortunate that Dave's on the project. Dave's just going, why?
Any other question or just the general questions to the people here you want to discuss? Okay, seems like it's a good meeting today, and we are approaching the end of the meeting. Like we still have a few minutes left, but I think people could use that time to have some fun by yourself. And start in this room, but it's still bright outside. And like tomorrow morning is still 9 a.m. at this room, and look forward to see you back. And Will, do you have anything to say to close?
No, thanks everyone for presenting today. Appreciate it.
Yeah, I'll go home and I'll get the transition to the historical. Look out what's going on the aerosols. Yeah. Peter.